Welcome to Hot Chips 31. Tutorial 2, RISC-V.
Hi, so let me introduce myself. I'm Krste Asanovic. I'm a professor at UC Berkeley. I'm also chairman of the board at RISCV Foundation and also co-founder and architect at SiFive. And I'll be doing the first part of the tutorial, which is to give you an overview of RISC-V and then to dive down and go over the basics of the ISA design. So the first part, I'm going to tell you about RISC-V in general, then a deep dive tutorial on the instruction set design. The following speaker, Bunnaroath Sou from SiFive, he'll be talking about the software ecosystem. Then the final session, we have 2.5 hours, one on the Berkeley open source RISC-V cores, Rocket and Boom, and the second on the ETH Zurich open source RISC-V cores, the Pulp project. So quite a great program. So let's get going. So RISC-V, who cares about instruction sets? We're at Hot Chips. You all know about instruction sets. But when I give this talk, I usually have to start by explaining why instruction sets matter. And I like to answer this question by asking questions. How can't Intel sell mobile chips, right? Right? Even when they staple $20 bills to the back, they still can't sell them, right? And the reason is they have the wrong instruction set. So they're based on ARM. The software ecosystem around the phones is all tied to ARM. So they have the wrong instruction set. They cannot sell mobile chips. Well, it's not all rosy for ARM. How come ARM guys can't sell servers? Well, the reason they can't sell servers is they don't run the AMD 64 instruction set. Now, what's curious here is how come Intel is making all this money selling servers based on the AMD 64 ISA? Right, well, you all know the answer, right? So Intel tried to move everybody to Itanium. That turned into Itanic. Thankfully, Microsoft and AMD collaborated to come up with a more compatible upgrade from 32 to 64-bit address space, the AMD 64, and Intel had a license. Intel's now quite happily making a lot of money with that ISA they licensed, and AMD is back in the action too, I guess. But going back in history, how can IBM still sell mainframes, right? Now what's great here is the IBM 360 is the oldest surviving instruction set. In fact, the 360 really defined the idea of an instruction set. It's when you define a hardware-software interface where you can have many, many different implementations, but all sharing common software interface. They really defined the idea of ISA. There's a big bet for IBM, and it's paid off for them. So the ISA is the most important interface in a computer system because it's where software meets hardware. So this is why it really matters in our industry. Now, in our industry, we have lots and lots of interfaces. And most of those are open. If you look across the field, like, for example, Ethernet. Right? Imagine if you had different standards for connecting machines together on the network. We used to have that, but basically Ethernet has taken over as an open standard. And the nice thing about an open standard is you can have free and open implementations or proprietary implementations. People get to choose where they get their implementations from. And if you look up and down the computing stack, we have things like databases, SQL, or query language, common interface. You can have open implementations or proprietary implementations. Graphics, OpenGL. You now have a standard. You can have open implementations or closed implementations. But down at the ISA level, we haven't historically had free and open standard. So why not? Is it because the proprietary ones are so good we're prepared to pay for them? Is that why? I don't think anybody would seriously argue that's the reason. It's just basically a historical accident that we don't have open ISAs. Now, you might say, well, who cares that the ISA is owned by some company? Does it really matter? It's not that important, maybe. But the problem is that your whole software world is built around these ISAs, and these companies come and go. There used to be a very big and powerful computer company on the East Coast called Digital Equipment Corporation, and they had some important ISAs, the PDP-11, the VAX, the Alpha. You may remember the glory days of Alpha. It was the fastest microprocessor on the planet. A lot of people excited about it, and it disappeared due to various mismanagement, business practices, or whatever that happened at DEC. It's now gone, and there's nothing you can do about it if you based your world on Alpha. If you wanted to go build Alpha chips now, you probably have to fight some IP holding company somewhere to go do that. And nobody really would want to do that because the software is no longer there. Intel, so obviously very successful, but you may remember all these other ISAs Intel had that came and went. i960, i860, Titanium, right? They've come and gone. MIPS, so MIPS is one of the classic early RISCs. They were sold to Imagination after a tortuous history before that. They've now been bought by Wave, and now they're thinking about opening up R6. But really, it's clear to most people that it's been on the decline for a while. And so if you had built your world around MIPS, you are probably moving somewhere else. Spark was another one of the classic early RISCs. So this interesting story here, so Spark back in the 90s, they actually opened up Spark v8 as an open standard. They made it an IEEE standard, the 32-bit v8. And there were a bunch of companies making Spark chips. But along the way, Sun got acquired by Oracle. The architecture was closed up again. And then more recently, Oracle has basically closed down all future Spark development. So Spark is gone as well. ARM. So ARM is obviously big, powerful, popular ISA in the industry, but there was some shockwaves in the industry when they were acquired by SoftBank and taken private for a large premium. So now a lot of people are now wondering what's going to happen with the ARM relationships given this investment by this big company. Right? So the big point about this slide is if you tie your software ecosystem fortunes to some proprietary ISA, there's not a lot you can do if that underlying company has some business mishap, more fortunes, or does something weird. Right? You're tied to this single entity. So that lock-in is bad. Now, the second thing about ISAs is engineers love them, so we have lots and lots of them. So there's many, many ISAs on one SoC. So you may think about, oh, this is a ARM SoC, for example. But what you're really talking about is the applications core that programmers see. But if you look around the SoC, you'll see graphics, image, radio, audio, security, power management processes. And it's not unusual to find you have over a dozen ISAs on a single SoC, each with their own compiler, software stack, and the poor software integration engineers have to make this thing work, right? So why are there so many? Well, one reason is that the apps processor is not designed to be the base of these various accelerators or these specialized processors. There's just too much stuff in that apps processor ISA, so you don't really want to use it as the basis for these other accelerators. The other problem is you cannot license it as something you're going to use in IP that you will then sell. So when you buy IP from outside, as is common for most of these SoCs, the vendor selling you the IP probably had to build their own proprietary IP ISA in order to incorporate into that block. And the third thing, which is the worst reason, is engineers love making ISAs and building their own cores. If you're a manager, do not let your engineers do this. It is a terrible thing to do. It looks great the first time you do it. I took the class with Patterson Hennessy. I know how to port GCC. I know how to do this. You can get things up and running. But then you have to maintain it, and you have to maintain it for a lifetime. And that's a big cost. And also, not everybody is great at designing ISAs, so please don't do this. Right? But these are the reasons why you have so many ISAs in one SoC. So the question is, do we need all these different ISAs? Do they have to be proprietary? Do they have to keep disappearing? Right? So the big premise behind the RISC-V project is what if there was one stable, free, and open ISA that everybody could use for everything? And that's really what we're trying to do in the RISC-V project. So let's go back to RISC-V origins, the background to RISC-V. So back in 2010, so my group at UC Berkeley, we do a lot of architecture research. We like to build chips. We actually like to do silicon, tape things out. We'd used a bunch of ISAs for previous projects. We were thinking about what to use next. The obvious choices would have been x86 and ARM because the software is there. That's the main cost in any project. But x86 is just horrendously complicated, and there's some IP issues if you were to put an open source x86 up there, right? Similarly with ARM. Back then it was ARM v7, and it's a pretty complicated RISC. Doesn't make much sense, that design, so we didn't really want to do that. And also in 2010, there was no 64-bit ARM. This was before v8 was released. And there's also the IP issues. We couldn't build an open source ARM core and share it with our colleagues in academia. That would not have been possible. So we decided to go off and build our own ISA. And so we started this 3-month project during the summer to do a clean slate ISA. And I'll give a shout out to the main designers, which is Andrew Waterman, Jan-Sub Lee, Dave Patterson, and myself for the principles behind RISC-V, though many, many people helped. Other people helped along the way. So that 3 months turned into about 4 years as we worked on the ISA design. Now, we didn't just sit in the room pontificating about ISA design choices. What we did in that time was did many tape-outs, many iterations, ported the compiler, ported the OS, and iterated over the course of time. And by about 2014, we felt it had stabilized enough that we were going to kind of freeze it and keep using it as it was. Now, just a little bit of history here. So the name RISC-V, and it's pronounced RISC-V, is the fifth major Berkeley ISA. That's where the name comes from. So here are the earlier RISC chips. Probably all of you are familiar with RISC-I and RISC-II, which are the chips that from Dave Patterson's research in the early 80s, and those are the chips for which he coined the term RISC, which has now become used generically for this class of architecture. Dave regrets a little that the follow-on projects, SOAR and SPUR, didn't stay with the RISC name. So to keep Dave happy, we went back and posthumously renamed those RISC-III and RISC-IV, and so we end up at RISC-V. And it's RISC-V, not RISC-V, because the first one, so RISC-I and RISC-II, they are not RISC-I and RISC-II, okay? All right, make that clear. So we had a lot of interest along the way, and we decided to make a deal and push this out, Hot Chips 2014. So I pulled up this old photo where a bunch of, some of you may remember, a bunch of students, Berkeley students, running around wearing these blue T-shirts. I pulled it out of to wear it today. Running around making a big stink about RISC-V and why everybody should use it. And we had tremendous interest, far beyond what we expected, as we pushed this out into industry. And the industry folks, though, were a bit worried about a university project being the basis for products, et cetera. So we then decided we needed to create something stable, so we created the RISC-V Foundation. So the RISC-V Foundation is a non-profit trade association that operates by itself, it's independent, and its main job is to manage the standard. So you can think of this as the RISC-V, it is the RISC-V standards organization. And the foundation we started in 2015, we thought we may get a dozen or so members, but over time, membership has just kept growing at a very fast rate. And so we now have over, I think it's actually more like 300 members, including something like 160, 170 companies and organizations, as well as individuals. And this membership is all around the world and in all different areas. So a quick logo slide. The membership includes a lot of the biggest names in semiconductors. So you'll see companies like Nvidia, Qualcomm, Samsung, Google, IBM, many, many big companies. Most of the big companies are already members of the foundation, and many of them are actively working on RISC-V related projects. It really is a worldwide phenomenon and across all parts of the industry, from foundries to software providers. So I just want to announce, so Krste Redmond joined as a CEO of the foundation earlier this year. She was previously vice president of the Z series ecosystem, and before that she led OpenPower. So she has a lot of experience in this domain of managing an ISA ecosystem. So we're happy to have her on board. So what does the foundation do? One of the main jobs of the foundation is delivering the specs and the standards and the compliance suites and certification. Also promoting the ISA, providing visibility. We're also working on packaging up training courses to help people learn about RISC-V, both universities and practitioners out in industry. Also a lot of advocacy and outreach about RISC-V, educating people why they should use RISC-V. And finally, for the members and customers, finding a marketplace where people can find RISC-V stuff out there, right? So go check out the RISC-V.org website to find out more about all these efforts, these initiatives. So how does RISC-V work? So the way RISC-V works is we have an ecosystem that is centered around the foundation. So the foundation manages the ISA standard. So the ISA standard is really the interface between software and hardware. So the foundation manages the spec, the go-to-model, compliance suites. Now, one thing that people are often confused about with RISC-V, RISC-V is not an open source processor. That's an incorrect statement. RISC-V is an open specification. There is no source code at the foundation. We took a stance at the foundation. We would be neutral regarding implementations. We would just focus on the specification. But because the spec is open, it means you can have open source implementations, and there are many of those. So later today, you'll hear about some of those, the Rocket Boom and the Pulpino cores, but there are many being developed all around the world in every possible hardware description language you can think of. People are writing and distributing RISC-V open source cores. RISC-V is not only about open source cores, however. There is a large and growing number of commercial core IP providers. So these are folks who provide commercially verified supported cores, just like you would get from any other softcore provider. In different series, these are all compatible with each other. So at this point, what I can say is RISC-V has more commercial core providers than any other ISA in history. And this number is just going up. And these providers are spread all around the world. Now, in addition to open source cores and commercial cores, you also have in-house cores. So quite a few companies have decided they would also build cores in-house. So examples are Nvidia, Western Digital, recent announcement from Alibaba. They're building their own cores in-house for their own products. Now, many of these companies are taking the approach of, I will use all of the above. Depending on the project, I will source a core from a commercial provider. I may consider an open source core, or I may build a core internally with my own team. And depending on the project, I'll do all of the above. And the great thing is, they're all compatible, and they use the same software stack. So this is the advantage of having an open spec. Now, on the software side, also you have the open source community, which has wholeheartedly embraced RISC-V, and it's been great to see RISC-V being adopted as a mainstream architecture in all the major open source projects. So things like GCC, Linux, binutils, FreeRTOS, all these, you'll hear a lot more about this from Bunnaroath's talk coming next about the RISC-V software ecosystem, but it's basically a well-supported mainline architecture now in all the open source tools. But again, it's not only open source software, there's a large amount of commercial software already available for RISC-V. So tools from companies like Lauterbach, Sega, IER, commercial RTOSs like ExpressLogic, Micriums, MicroCOS. These are also available, commercially supported commercial software for RISC-V. So if you're thinking RISC-V is only open source, that's an incorrect statement. RISC-V enables there to be a thriving open source story around RISC-V, but there's also a lot of commercial support as well around RISC-V. So why is it so popular? So I think engineers sometimes don't see the forest for the trees. It's not happening, this movement is not happening because some implementation is a bit faster or a bit lower power than some competing core. That's not the reason people are excited about RISC-V. This may be true in some cases, but that's not the big deal. The big deal is the business model has changed. So now, previously, when you were trying to build a chip, you would go have the vendors bid to put a core on the SoC. They'd all bid, you'd pick one, and then you would get their ISA. And then if you're successful to a second generation chip, you probably stuck with the same vendor, no competition. Now you pick the ISA first, I'm going to use RISC-V. Then you go shopping for where you're going to get that core, and you have a lot of freedom. You can pick amongst the vendors. You can use an open source core, you can build your own core. Another part about RISC-V people appreciate is we designed it, as I'll talk about later, to enable you to add your own stuff without asking permission. In effect, everybody gets a RISC-V architectural license for free. And that's also very exciting to people. They can innovate while still using the standard software stacks. Now, RISC-V is still new. We've been working on it now for 9 years, I guess, from the very beginnings. But in terms of commercial uptake, it's relatively new. And if you're worried about there's some feature, there's some PPA design point that's not there, just wait. All these things are getting fixed. There's so much momentum behind this that whatever issues you think there are with RISC-V, they're probably going to get fixed sometime soon. OK, so at this point, our modest goal is just become the industry standard ISA for everything, right? And we're sort of moving along that tangent, right? Just to give you some idea, I'll go through a few quick slides on where things are. In terms of industry adoption, big companies already adopted RISC-V for deeply embedded, what we call minion cores on the SoC. So some examples, Nvidia announced all the future GPUs are going to use RISC-V microcontrollers. 2017, Western Digital announced all their product is going to move to RISC-V-based SoCs. There are many other big companies waiting in the wings, just getting their ducks in a row, before they also announced a similar kind of transition. Basically, CTOs everywhere, it's not about if we'll use RISC-V, it's more about when and where we're going to be using RISC-V in our products. It's becoming a normal design choice. So a lot of embedded IoT, RISC-V is already a strong competitor. Other areas also go in RISC-V. This year, you'll see, you may not be aware, but there will be millions of SoCs with RISC-V cores on them being produced this year. This is really the first year of mass production. Like SiFive, we announced over 100 RISC-V IP design wins. Andes and the company they designed announced 21 last year, 60 this year. So the point is, you won't get fired for choosing RISC-V, right? So it's a pretty safe design choice. In a few years, you might get fired if you don't choose RISC-V. We're not quite there yet, but we'll see. One of the phenomena is replace second-tier ISAs. So there are many companies who had this proprietary ISA. They had a limited market for companies who were prepared to pay less to get a core that maybe wasn't as well-known, well-supported. But all those companies are seeing there's a much bigger market if they go with the RISC-V standard. And so some examples, Andes, Codasip, Quartus, C-Sky. These are all companies that had their own business with their own ISA. They've now moved and are now providing cores based on RISC-V. And the message is, if you are a soft core provider, no matter how big, you should have a RISC-V product in development, because this is what customers will be asking for. Startups, many startups use RISC-V, a few ones here. One thing about startups, we don't have to tell them about RISC-V. Once they go shopping for processor IP, they find out about RISC-V very quickly. So it's been very successful in the startup space. A lot of new ideas, new application domains are coming to RISC-V first. Now, I mentioned this already, the commercial ecosystem, companies like Lauterbach, Micrium, Sega, these guys, they're developing tooling because there's demand. And this is a leading indicator. If you're wondering, are big companies working with RISC-V? Well, the people who can afford this tooling are requesting this tooling, and you can see that in these companies providing products now to service that demand. So serious commercial tooling for RISC-V. Government level. So this is an unusual thing. India adopted RISC-V. They funded 2 big projects around RISC-V. The US, DARPA mandated the use of RISC-V in security research. In Israel, there's a startup incubator around RISC-V. Shanghai municipal government is funding startups around RISC-V. So a lot of government level support for RISC-V. And the reason is quite simple. If your country wants to control its information infrastructure, you need to be able to build your own cores. And RISC-V enables you to do that while keeping the big software ecosystem. And also, if you want to promote your own indigenous semiconductor industry, a lot of countries are worried about trade imbalance. Semiconductors are a growing part of the value of most products. So they need to somehow source at least some of their semiconductors locally. So these are also reasons why government's behind RISC-V. Education. So I'm a professor, and I like to teach RISC-V. And Dave, my colleague, thankfully, he managed to convince John as well to translate this classic textbooks, computer organization design, and the quantitative approach. Both those are now RISC-V editions, and there's also a good reader Dave Panison wrote with Andrew Waterman. So this is just part of it, but there's a lot of curriculum around RISC-V now, and this is spreading through all the top schools. So basically, in a few years, you'll basically find that almost every computer engineering undergrad around the world will have learned RISC-V at school. It'll just be VISA you learn. When they come out of industry, is what they're going to expect to use. And so really, RISC-V, the openness here lets you complete this innovation cycle where what students use at school, they immediately start using out in industry. Industry hits a problem, tell researchers, go work on it. Researchers can work on that problem. And the tech transfer is very quick and seamless because everybody's using the same thing. So having this open ecosystem allows this very virtuous cycle that I think is going to be key to innovation going forward. So that's kind of my overview of RISC-V and where it is. And I'll jump now and do a deep dive. So, OK, that's great. But what is it? How is it designed? How does it work? So the second half here, I'm going to dive into, give you a RISC-V ISA tutorial. So first of all, what's different about RISC-V? One thing is we do like to describe it as a boring RISC. If you've ever read a RISC ISA manual, RISC-V should be very familiar to you. That shouldn't be a surprise because it is the 5th in a long history of developing RISC out of Berkeley. But some things that are different are it's very simple. And there are many things out there called RISC right now which are not that simple. But RISC-V was designed to be very simple, and it's far smaller than other commercial ISAs. We also have a very clean slate design. We try to avoid making any architectural decisions based on assumptions about the microarchitectural implementation style. There's been some classic older ISAs that the designers were fixated on in-order designs, or they were fixated on out-of-order designs, and they consequently made the ISA less suitable for one or the other. We also try and be independent of technology. One thing I like to remind people is RISC-style designs, which to me is a register-rich load store architecture. Really, I think it was Seymour Cray back with the 6600 really showed that style of design. This class of design has outlived Moore's law, right? Moore didn't write his paper until after the 6600 came out. Moore's law is dead. RISC designs are still there, right? So it's a very long-lived design. It'll probably last for a few more technology generations. So we designed it to be modular. The project in which we designed RISC-V was all about custom accelerators and specialized cores. And so we designed the ISA to have a very small base ISA that was nevertheless enough to run a full compiler stack and then left a lot of space to add your own extensions. But we also defined a bunch of standard modules that you plug in to give you a more or less general purpose ISA if that's what you need. So there's a very large available opcode space. I will talk about the variable length encoding as well to enable you to add all kinds of instructions to the ISA. One other big deal is it's stable. So we designed RISC-V. We didn't quite realize how important this was when we did this. I think, as university professors, we wanted it to be stable so we didn't have to keep updating our slides every year. But out in industry, there's a real need for, it's good that the ISA doesn't change all the time. We have no economic incentive to keep asking you to license the 0.2, 0.3, 0.4 versions, right? Stability's fine. If you embed processors in concrete, you still need to find tools for that processor 50 years from now, right? So stability to us is a very important feature. So that base and the set of first standard extensions, they're all frozen and ratified now, and basically they're the same as when we released them in 2014 at that Hot Chips event. And when we enhance the ISA, we do it by adding a new module, not by iterating on the existing pieces and changing them. One of the big differences is designed by the community. So it's not just one company deciding what goes in the ISA, it's that whole membership of the foundation who are driving the ISA development, and they decide on the roadmap as well. What's important, what do we work on next? So let's look at the ISA. So in the ISA right now, there are 4 basic integer ISAs. So there actually isn't a RISC-V ISA. There is a family of related RISC-V ISAs. So RV32E, RV32I, RV64I, RV128I. So that number is basically address space size, 32-bit, 64-bit, and 128-bit address space. When we first designed the ISA, the 128-bit address space version, we put in partly as a joke. There's a classic quote from one of the early ISCAs. The only mistake you can't recover from in ISA design is not enough address bits. So we decided it fit into the template, we would add the 128-bit encoding. Subsequently, there's been more interest than we imagined. If you look at the amount of solid-state, non-volatile memory going into data centers, it's already hitting hundreds of petabytes, which is actually, and people are building fast load-store communication networks to access that hundreds of petabytes. So we're going to run out of 64-bit address space pretty soon, maybe this decade, next decade. So 128-bit may be needed sooner than we thought. But also, one other thing we did for the very low end, the standard ISA has 32 integer registers. We also defined the E variant, RV32E, only has 16 integer registers for low-end microcontrollers. Now, this base integer ISA only has actually less than 50 hardware instructions, and that runs all the tools and provides a lot of features. You can have PIC, dynamic linking, you can run Linux with less than these 50 hardware instructions. Now, on top of that base integer ISA, you add these modules, which are the standard extensions. So that includes integer multiply divide as an extension, atomic memory operations, single, double, quad, floating point. So these letters indicate what else is added to the ISA. G is an abbreviation we use for IMAFD. It's kind of meant to signify a general purpose ISA. And all of these use a pretty standard RISC encoding in a fixed 32-bit instruction word. We froze these in 2014. We ratified those this year with the foundation. So everybody in all the membership has agreed on this now. And these are now going to be supported indefinitely, those instructions. So just to talk about these ISA strings, you'll see these strings pop up when you're working with RISC-V. So RV32I is a base ISA, has a 32-bit address space, only the basic integer instructions. Something like RV64IMAFDC, also known as RV64GC, that's a 64-bit address space version with integer model divide, atomic, single, double, precision floating point, and compressed. RV64GC is what the standard Linux distributions assume your core has. So one thing to realize about RISC-V, there's the whole embedded world, which wants everything highly customized. There's also the Linux platform world, which doesn't want any difference at all. And so in that space, RV64GC is what the various distributors have decided is the standard thing they'll supply binaries for. So you can still compile Linux for any of the other variants. RV32EC is another example. This would be the 32-bit address space with only 16 integer registers and only basic integer ops and compressed ops. And a full-blown RV128 IMAFDQC has a whole bunch of features, right? So this is just to give you an idea what these strings look like. You'll see those popping up in the discussions today. So the unprivileged state in basic processor, they have different widths, and we give that parameter a name, xlen, means how wide are the X registers, which are the integer registers. They can be 32, 64, or 128-bit, depending on the base ISA. There's a program counter. There are 32 integer registers, X0 through X31. X0 is a hardwired 0 register. The RV32E variant only has 16 registers, X0 through X15. There's, optionally, if you have a floating point extension, it adds 32 floating point registers, F0 through F31. This is IEEE representation. And the different extensions mean that FLAN is either 32, 64, or 128-bit wide. So that's how wide your floating point registers are. There's also a floating point status register, which has the rounding modes and exception flags, just as in most other architectures. So the standard base ISA, the encoding we picked to be very vanilla and extremely easy to decode. So the base ISA and those standard extensions are all a fixed 32-bit instruction format that's aligned on a 32-bit boundary. One thing we did was make RS1, RS2, the two source registers, and RD, the destination registers. They're always in the same place in every instruction. So a lot of other ISAs do some tricks that mean you need to mux those. We wanted to keep these constant to help high performance implementation, simplify the circuits. Also, everything is always sign, the immediate is always sign extended, and it's always sign extended from bit 31 of the instruction. So the immediate encoding is sometimes scrambled a bit to make that happen. It's a very simple ISA. So simple, here is the base complete ISA for RV32I. So there are 40 instructions in the unprivileged architecture, and that's them there. Some of you in the front rows can probably read that. You basically have the load up immediate, PC relative add, jump and link register, branches with comparisons built in, load store bytes, integer ops with adds, logic ops, shifts with both immediate, register variable values, fence, memory ordering, equal, and e-break. And that's basically it. So, and you'll notice the very regular instruction format. You know, it took to heart the very RISC idea. It took a long time to make it this simple, is what I say. And on top of that, you have the multiply divide extension. This provides signed, unsigned multiplies. They return only one XLAN bit of the product, but there are instructions to return the lower XLAN and also the upper XLAN of the two XLAN products. You can get multiply and multiply high to get both halves of the product. And we also support signed, unsigned, and signed, unsigned multiplies as well. And we have a recommended sequence that will let a microarchitecture fuse and give you both the upper and the lower XLAN with a single hardware multiply. The RISC-V memory model. This took a bunch of work. We had a dream team of people working on this. We have a base weak memory model, VWMO, it's called. It is multi-copy atomic, meaning that when a store is made visible outside of one thread, it is visible to all other threads at the same time. And this dramatically simplifies software's view of the world. And it's similar to ARM's revised V8 memory model. What's curious is while we were working on the RISC-V memory model, around the same time, ARM changed theirs and made it more strict, realizing much of the same things we did about software usability. We also defined an optional TSO extension, the total store order. This is strictly upwards compatible with RVWMO. So if you have code that expects RVWMO, you can run it on a TSO machine, no problem. And this is similar to the x86 memory model. This provides a much simpler model for programmers, even if it comes at some hardware cost if you want to build a high-performance implementation. For the memory model, we have complete both axiomatic and operational formal models available at the memory model. So the atomic extension there's two classes of atomic operations we add. AMOs, which are fetch and op. So you can do fetch and add, fetch and or, fetch and max, fetch and min on a single word in memory. There's also load reserve store conditional with a restricted forward progress guarantee for certain sequences. So this allows us to implement the equivalent of compare and swap with a short sequence. The reason we did this, we didn't want to have compare and swap in the architecture as it's kind of ugly to implement. So we went with load reserve store conditional, but we had the forward progress guarantee to make it behave better than a load reserve without that guarantee. The other thing with the AMOs, they can be annotated with extra ordering bits. There's a acquire and a release bit on each of these operations, which allow you to add extra ordering on those AMOs inside that instruction without needing a separate fence. And these are very precise because they just talk about this one AMO. floating point extensions, they add this second set of 32 registers. The width is flen. Basically, if you add the double, that implies you have the single. If you add the quad, it implies you have the double and the single. The registers are as large as needed to hold. Each register holds one floating point value. One trick we do is if you write a narrower result to a wide register, say you write a single precision result to a machine with double precision wide registers, we do what we call NAND boxing. So we extend the upper bits with all ones. And so if you accidentally access that as a double after having written a single there, it'll appear as a NAND to the double operation. Also in the floating point, we have non-destructive fuse multiply adds to support IEEE 754-2008. And so there's a new instruction format that has 3 sources and 1 destination. So variable length encoding. So the standard extensions, the ones we've been talking about so far, the IMA FDQ, those are all a fixed 32-bit encoding that can all live on that could all be aligned on a 32-bit boundary, classic RISC design. But when we were designing RISC-V, we were very conscious about the need for A, compression, and B, for extending the opcodes to support wider instructions. So we deliberately designed the ISA to support a variable length encoding scheme. So the regular 32-bit instructions all have the bottom 2 bits 1, 1. That means it's 32-bit or greater. If the bottom 2 bits are not 1, 1, then it's a 16-bit instruction. And when you add the 16-bit instructions, you retain the existing 32-bit instructions. They don't change, they're encoding. All that happens is now they're allowed to be aligned on any 16-bit boundary as well to get better code density. So we don't have a separate 16-bit instruction mode or a separate compressed instruction mode. The 16-bit instructions are just an add-on to the base ISA, and all they do is mean that the existing instructions can be aligned only on a 16-bit parcel. Now, the one cost we paid for this was even in the base ISA, when you are not using 16-bit instructions, the relative branches are defined in terms of 16-bit parcels. So you kind of lose 1 bit of range, but in return, you get this variable length encoding added as a simple extension on top. Now, the encoding space is defined to also support 48-bit, 64-bit, and much longer instructions as well. And all that can be determined from the first 16-bit parcel you see when you're doing the fetch and decode. So it's relatively easy to decode these variable length instructions. So the compressed instruction extension makes use of this and adds a bunch of 16-bit code. And compressed code is important both for static code size in low-end embedded systems, but it's also important for dynamic instruction footprint in high-end systems. The C extension, we made it very simple. There's basically 2 address forms that use all the 32 registers. There's also 2 address forms that only use 8 of those registers, X8 through X15. And we basically take the most common 32-bit instructions and give you a 16-bit version of those. And the other simplification we made is the 16-bit instructions, they all expand 1-to-1 to a 32-bit instruction. This was kind of one of those simplifying rules we made. And this has been very useful because, in fact, the compiler doesn't even need to know about compressed. The current toolchain, all the compression is actually done in the assembler and the linker. When you're building an implementation, the decoder is only a few hundred gates, several hundred gates to build that decompressor. So it's actually very, very simple hardware. And in practice, we see about 25 to 30% code size savings by using the compressed instructions. So that's a quick tour of the ISA. Here's a look at the whole set of things. So this is not just the base ones, but adding on the multiply divide, the atomics, the floating point, the compressed, different widths. So basically, you can fill out this card. You end up with a single sheet of paper, which is the RISC-V green card. And this is Mark Hill has this great joke about you can tell it's a RISC when the manual doesn't need a staple, right? So this is the RISC-V green card that has all the basic ISA on there. So when we went out and sold this to people, say, hey, we have this great thing. It's really simple. Out in industry, it's kind of funny because simplicity really breeds contempt. Like, how can this simple ISA compete with these industry monsters? Right? Obviously, you guys know what you're doing. That's a nice toy academic ISA. Nice to play with, nice to teach, but to do serious work, you need a serious ISA. You need at least 10 times as many instructions, right? So how do you measure ISA quality? We're used to measuring implementations. Back in the old days, there were some measures we'd use. Static code bytes, dynamic code bytes you fetch for execution. Another measure we try to come up with is microarchitectural work you generate during execution. How many primitive micro-ops do you need to run the code that you fetched? So in terms of static code size, both in 32-bit address and 64-bit address-based versions, we do very well. And particularly in 64-bit address space, where it's pretty much the only ISA that has that compressed instruction. So this is on spec-int, looking at code size. The static code size is very competitive with all the other industry ISAs when we add the compressed extension and do some compiler optimizations. In terms of dynamic bytes fetched, if you look across there, you'll see that it's already much better than x86, 64, and also ARM in terms of dynamic byte fetch, even though we don't have support for vector operations. It turns out the few cases where we do a little bit worse, the other ISAs are using vectors and SIMD to cut the number of instructions they execute to run the program. Once we add the vectors, RISC-V will have an even bigger advantage in dynamic bytes fetched. Finally, how much work do you do? Like in machines now, people do both these techniques. You take a single macro instruction and break it into multiple internal micro-ops, or you take multiple macro instructions and fuse them into one internal micro-op. So it's not that easy to tell how much work is the machine doing inside. So in RISC-V, we noticed that a lot of the things that people wanted to add new instructions for, we could instead do by taking existing instructions and fusing them. So for example, doing a scaled shift and add on an address. We can just do that with 2 instructions and fuse them. Or an index load, we can add the 2 registers and fuse it with a load that takes the sum as the address. Now, what's interesting with the compressed extension, a lot of these instructions are 2 bytes, so we can effectively create new 4-byte instructions that are the fusion of 2 2-byte instructions. And the cool thing here is that that doesn't complicate the ISA. A simple implementation can do them one at a time. A high-performance implementation can fuse them and do them as a single op in the decoder. So we're trying to avoid growing the ISA where we could just have done it with simple macro-op fusion. So we did some numbers here, and this is showing you how many relative to, so 1.0 on this graph is the number of instructions an x86-64 would execute. The first purple bar is showing you when that's cracked into micro-ops, what the internal performance counter tells us it's doing in terms of micro-ops, which is 14% more than the base instruction count. Similarly, ARMv8, for example, has some instructions that are cracked into micro-ops. A little harder to get that out, so we had to do some estimation. And similarly, we took the RISC-V design and then added the macro-op fusion. So by doing this, we figured out basically all the machines are doing roughly the same amount of work in terms of microarchitectural work. But remember, we have a smaller code size, smaller dynamic bytes fetched, far, 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 far smaller instruction set manual, right, to get the same level. So in terms of quality, that's why we like RISC-V. Now, it's not just us. Many companies have now done their evals. I like this quote from Dave Ditzel. Esperanto was going to use their own ISA, and they learned about RISC-V, decided to do an eval, and lo and behold, it was very competitive with what they had been expecting to do. They're not the only ones. There's a public talk from Nvidia talking about their decision to use RISC-V. They did an eval against their own core and commercial ISAs and picked RISC-V. Many other companies have done the same studies. So people now, initially it was, great, this is free. And after a while, it's like, this is actually pretty good. So, and it's simple. Now, one thing about RISC-V, we designed it for extensibility, customization, cover this huge space. And some of the things people worry about is, isn't it just going to fragment? Are there not going to be 10,000 different RISC-Vs in the world? And I like to address this by making the distinction between fragmentation and diversity. So fragmentation is when you do the same thing in 2 different ways for no good reason, right? That's just painful, awkward, waste of resources. And my example I like to quote here is cars, right? So some of the world drives on the left, some of the world drives on the right, right? No good reason to pick one side or the other. I just came back from India. They don't care about which side they drive on. They pick both sides. But the steering wheel is on one side of the car, right? Doesn't help anybody to have these 2 differences. It's just an arbitrary decision. It just means you have to support twice as many kinds of car. Diversity, though, is when you're solving different problems. Like if you want to go across town a couple miles, bicycle is a great solution. You want to carry 500 people across an ocean, you kind of need a big jet, right? So we want to support all these different use cases, but where things are common, do them in the same way. So to help understand this, how does RISC-V work? How is it standard? How is it customizable? We say a standard piece of the ISA is something the foundation has defined. Reserved is space the foundation says, we're going to use this in the future. If you use this, you're going to probably be stomped on by something that's coming down the pipe later. But custom space, we said, this will never be used by the foundation. Feel free to use this part of the encoding space. So if you build some core, so this is an abstract view of the reserved instruction space. Custom space is over here. You build something, you'll take the standard modules we have, IM, AFD. Then you add your custom stuff over there. This is all fine. All the standard software only talks to the standard extensions. It doesn't care about those other custom encodings you added. And usually those are used in a few kernels and a few type places in your code. That's where you'll be using those custom libraries. So the point here is you can use all of the standard software, all the standard tools, linker, everything else. You're just adding the custom stuff over to the side. You could even go further and say you use less of the standard ISA and decide, I'm going to use this reserve space too. Well, you can do that. It's not advisable. And you can do that because you can still use the standard software on that subset that you use. So all the compilers and everything are parameterized by ISA string. You can tell it which pieces to use, and it'll compile for those things. Leave that other space free. The danger here, though, is sometime in the future, you may want to use another standard module that's going to conflict with a thing you built. So ideally, you would stay in the custom space. And there's plenty of custom space because we have variable length instructions, right? As well as a very small base ISA. So we talked a bit about the unprivileged architecture application code. Let's talk about the privileged architecture now. So in RISC-V, for one thing, we designed it so this is the current privileged architecture, but the whole thing could be replaced with a completely different privileged architecture. And actually, I think this is one place where we need a lot of innovation. But in RISC-V terms, we wanted to get going using a standard model so we could get standard OSs ported. But I think there is space for a lot of innovation in privileged architectures. But for now, I'll describe the existing RISC-V privileged architecture and how it's used with standard software stacks. So there are 3 privilege modes by default: machine mode, supervisor mode, user mode. And machines support either only machine mode, or an embedded system with protection would have machine and user, or a full-blown demand page virtual memory system would have machine mode, supervisor, and user. We're also working on a hypervisor, which would run in a modified S mode called HS. This is designed to support type 2 hypervisors like KVM, but it can also support type 1 hypervisors and also supports recursive virtualization. But for now, most systems are just implementing MMU, MSU kind of systems. So in simple embedded systems, everything's flat, bare metal, no protection or translation. This is very low cost. This is kind of microcontroller that's not connected to anything is what you might use simple embedded M mode only systems for. Now, secure embedded systems, you want to use separate user mode, which is less privileged. And we have the concept of physical memory protection, which is common in other architectures too, but it's quite a flexible scheme. It allows the machine mode monitor to isolate itself from the user mode tasks. But in addition, we can delegate interrupts to user mode. So we can have interrupt come in, but the handler runs directly in user mode and privilege. And the goal here is to reduce the size of the trusted code base in the machine mode monitor. You don't have to have the interrupt handlers running in the monitor, except for the secure ones you want to do down there. The physical memory protection is designed to be quickly changeable and swappable, so you can have multiple different application security domains on the core. You can just swap those in software. And that was part of the design to provide a very flexible security model. Now, we also have full demand page virtual memory if you support the supervisor mode. And we designed this to support Unix-style, classic demand page virtual memory systems. It's a 4 kilobyte page size. We also support mega pages and giga pages, larger page sizes. This is a very vanilla virtual memory system. We designed to be very straightforward so we could quickly port OSs over to it. And the size of virtual address space varies depending on architecture or choice. RV32 has a 32-bit virtual address space. Actually supports a 34-bit physical address space. On RV64, the base one is SV39, a 39-bit virtual address space. But we also have 48, 57, 64-bit virtual address spaces. They just add more levels in the page table. So they just increase the time of a TLB refill. Now, one interesting difference in RISC-V land is most systems had either physical memory protection or an MMU. Like in RISC-V land, you always have the physical memory protection because we always want to have the machine mode monitor isolated from whatever else is running. So when you run a supervisor mode operating system, it is contained by those physical memory protection registers. So this gives you basically physical partitioning on the bare architecture. And even the hardware page table walker of the supervisor mode is contained within those PMPs. So we cannot get outside that box. And again, we provide interrupt delegation, so interrupts go directly to that supervisor process without going through that security monitor. So you can always have the secure mode running underneath. I already talked about the hypervisor. This is work in progress. This is coming along. There is a draft QEMU implementation with an early port you can go take a look at. RISC-V and security. So there's been a lot of interest in RISC-V and security. Part of it is we kind of designed it from the beginning to support this security monitor. And also, people often ask themselves this question, what am I going to trust? The simple free ISA that has open implementations, and I can see the security system, or some complex ISA that has an NDA-only security system. Answer is pretty clear, and so RISC-V has already become the center of a lot of security architecture research. And the goal here is we designed it with a small set of primitives. There's not a single pre-bundled execution environment, trusted execution environment we provide, because every use case is different. We have such a wide range of use cases. You want to optimize for the threat models you will actually see and tune for the cost and power of avoiding those threats. So we designed it to have a set of primitives instead of prepackaged single-point solutions that don't tend to work well across the space. And so it's being used for everything from embedded security to supporting remote cloud enclaves already in RISC-V land. I mentioned the ISA, the foundation. Just to give you a snapshot of status, all those base and initial extensions are not only frozen, they're now ratified, which means that membership is agreed. This is RISC-V. Debug spec, portion has been ratified. The memory model has been ratified. The privilege spec, which is one version of this, has also been ratified. Formal model is now available. And we're working on new stuff. So the base is all there. The foundation of the foundation is there. They've all been designed, looked at, argued about, agreed upon, and now ratified. So that spec is done. We're now working on new things, including the vector specification. And there's a lot of other new ISA modules in development at the foundation. The one thing about this is a member-driven ISA roadmap. So it's driven by members coming along and saying, we want to work on this. Let's set up a task group. Let's get the experts involved. Let's try and push this design forward. So one thing I'll just briefly mention is the vector extension. So this adds 32 vector registers of variable length depending on the implementation. So this is a vector length agnostic design. It supports a wide range of memory operations, unistride, scatter-gather, segment load stores, structure load stores. For each set of operations, it's also designed to support mixed precision particularly well, so 16-bit times 16-bit into a 32-bit accumulator, for example. And it's designed also to be a base for further extension with new data types and new kinds of operations. So this is, you can go get the spec and download the software and play with this right now. So to finish off this section, I just want to ask you all to join the foundation and engage in developing the ISA. This is a snapshot of the current different working groups and task groups within the foundation that people are working on to add new stuff to the ISA. Okay, that's it. Just about time. I can take a couple questions while we get ready for the next speaker.
Thanks for a great presentation. One question I have is when the first edition of Professor Patterson's book was published, it had an instruction set for a machine called the DLX, and it was an open ISA at that point. So I was wondering why it did not gain traction at that point, and we had to wait so long.
Yeah, so DLX, actually the OpenRISC project, which I didn't mention, they actually took basically DLX, turned it into a core, and that OpenRISC project got some traction. It was used somewhat. I think some of the issues, we actually looked at that. They didn't have a 64-bit version when we looked at this. They had a bunch of clunky old 80s RISC problems like delayed branches, things like that we didn't want to use. Also, they had fixated on the core as the artifact instead of the ISA as the thing to work on. Also, I think just in terms of timeline, people are now ready. Like, it's more of an SoC environment now instead of a microprocessor environment. So back then, you were kind of competing to build a microprocessor. Now it's more about a core that goes on an SoC. So that's why I think it didn't take off.
Thank you.
Alan Cantle, Molex. Earlier today, we've been hearing about differing number formats, different precisions in the floating point, etc. You mentioned IEEE support. Does this architecture support the potential for these newer number formats?
Yes, I think about every other day I get an email from somebody with their POSIT proposal, or X, numeric format. Yeah, there is space to add custom data types in the architecture. There's a place you can add. Floating point will now be this format, for example. Judging the amount of email I get about POSITs, I think there's a lot of active development of it. There's a lot of push. I don't see much pull yet, but yes, there's a lot of active work on it.
So thank you for an excellent presentation. I started with the MIPS book when it was like in alpha, and I had so many questions when you talked, and now almost all of them are solved, but I still have like a few minor ones. First, what is the business model of the foundation? And the second, all related, is you mentioned, what about DSP extensions like Altivec or vector extension? You did say something about it. And finally, about fixed point operations.
Okay, so the business model of the foundation, it's a non-profit trade association. So there's a membership fee, like universities and individuals are free to join now. But companies pay sliding scale based on their size, or they can join at a premium level. It's basically member fee only. There is a lot of active work in different SIMD extensions. So the P extension is designed for small integer-only data paths with a few fixed point operations, where you divide the integers up. The V extension supports much larger data paths, everything from 32-bit to thousands of bits wide data paths, and includes fixed point as well as floating point in the design already. The spec is available. You can go get it from GitHub, from the RISC-V.org website to take a look at the vector spec. Also, the simulator and bin utils are available for that vector ISA. So I encourage you to go take a look at the spec and the tools.
Satoshi Matsushita, New Malaysia. Last year or the year before the previous year, there was a discussion about sideband attack like Spectre and Meltdown. And there was a discussion that we need to have that specification to avoid that. So do you have any idea about that?
Yeah, so one thing is those attacks are not ISA specific, they're microarchitecture-based attacks. So if you build a RISC-V core with the wrong microarchitecture, you would also be susceptible to those attacks. So there is interest, there is a security working group. We are looking at things like timing domains, timing isolation, so you can declare the equivalent of a timing fence. Instructions after this fence do not depend on, the timing does not depend on anything that happened prior to that. And there's different ways to implement this. So yes, we have a security standing committee. This is a hot topic within the RISC-V community, yes.
Thank you.
So Charlie gets a quick question, and then Krste takes more questions during the break.
Okay, the question is, who gets to vote on what happens in the foundation, which is the kind of polite way of saying, is it gameable?
We try and make it not gameable. One way of doing that is encouraging, when you have 100 and something companies, and many of them have a vote, there's only one vote per organization.
Is it an equal vote, regardless of level?
Okay. Yeah. Okay. Thanks. I'll be around during the break as well, so I'm happy to field a lot more questions then, but I'd like to move on to second speaker. It's Bunnaroath from SiFive, and he'll be telling you about the current status of the software ecosystem around RISC-V.
Thank you. Okay. Hello. My name is Bunnaroath, and I am a software engineer at SiFive. I'm very sort of honored to have the opportunity to be able to come and give a speech here. In particular, giving an overview of the RISC-V software ecosystem. But I have to admit, this is my first time doing this, so I'm a bit nervous. Having said that, let me start off by sharing with you this particular slide. 2 years ago, when I first looked into RISC-V and SiFive, the RISC-V Foundation has around 60 members. Now, 4 years after the public announcement of RISC-V, that number has increased to over 230 members already. And with that, you can imagine the sense of urgency needed for software support. ranging from tools like compiler, linker, to libraries, operating system, application, and so forth. So with that in mind, let's start with tools, in particular the open source tool. Because RISC-V is an open architecture with open ISA, this actually promote and foster a lot of collaboration among well expert in the area as well as company, as you can see here, which further emphasize that open standard does work. As a result, tool chains like the GNU toolchain was able to be able upstream with the RISC-V support, like in the case of GCC and BinUtil, as way back as May 2017. And similarly with newlib and glibc library as well, including the debugger early last year. So what does this mean for normal usage? Well, for RISC-V, there are a couple arguments added to the GCC command line. In particular, the one start with -m. So there are three of them. The first is the march, which allows you to specify what ISA, that is, what architecture to target for. It allows a way to control which instruction set and register to use, and determine the set of implementation a program can run on. The toolchain supports three base ISA, and this actually comes from the RISC-V user privilege spec itself. The first being the RV32I, where a load and store ISA has where a load store ISA with 32 register, that is 32-bit wide. There is also another ISA, which is the RV32E, and that is more intended for the embedded. In that case, it simply provides a subset of the RV32I. There is also an RV64 that provides the 64-bit flavor of the RV32. Combined with this, there's also some extension in that, and this extension follows the ISA as well, where you can add an M, an A, an M for integer and multiplication and division, an A for atomic instruction, an F, which is for single point precision floating, D and C for compression as well. So these combine to give the ISA string that you can use when you generate or when you compile a particular C code. So as you can see, some of the examples that you could do is like an RV32I M with the extension M, which means that this particular architecture supports integer multiplication and division. Or on the other hand, you can say an RV64I MAFDC, which basically support all the extension. So what does actually mean? Well, let me sort of walk through a simple example in this particular case. I have a C code that basically take two double, and it simply return the multiplication of the two arguments. Now, when you actually compile this particular C code with the MArch, with the RV64 and I guess I can't see, IMA FDC, because that implied that this particular processor or architecture support a precision double floating point. The instruction being generated is it's one single instruction. This does not, however, preclude for a process that does not support double point precision. Or in some cases, you don't want to use the hardware implementation, in which case an emulation function get used. As I mentioned, the other argument to the RISC-V command line is the MABI, which is provide an ability to select the ABI for the target. What that means is simply it provides the ability to control the convention, which is what argument are passed into which register, and the layout of the data memory itself. So there are two integer ABI and 3 floating point, which can be combined together for you to select which appropriate library for your particular target. So in the case of the 2 integer ABI, it follows the normal standard ABI, where an ILP32, in which case the int, the long, and the pointer, they're all 32 bits long. A long is a 64-bit type, and a char is a 8-bit, and a short is 16-bit. On the other hand, an LP64, a long and a pointer are now 64-bit, which is conventional, just like any other architecture. But what becomes interesting and specific to RISC-V is that you can tag on the 3 floating point option to that, where if you don't want any floating point argument to be passed to the register, then don't give any extension. But if you want a floating point, like a 32-bit or smaller floating point argument to be passed to the register, then in addition to the, for example, IL32, you can put an F there. Similarly, for D, which defines that it is a 64-bit floating point. Here is some example that you could actually do. For example, in the first case, it indicates that a hardware floating point instruction can be generated because you have the F and the D in the MARC ISA string, and a D for at the end of the ILP32, which indicate that the floating point argument can be passed to the register. On the other hand, in the second case, because you didn't specify a D, then no floating point instruction can be generated, and no floating point can actually be passed to the register. And similarly for the third one. On the other hand, if you try to use, let's say, as in the last one, where you specify an RV32 IMC, but then your ABI now, you specify either a floating point or a double precision floating point. In that case, that would be an illegal, and your compiler and linker will complain about that. The last M argument to the RISC-V command line is for tuning, which is to inform the GCC that some performance of each instruction for a particular target need to be done. Now at SiFive, we do have some tuning model. So one of the advantage or benefit of RISC-V toolchain is this concept of relocation, and relaxation. But before I jump into the relaxation part, let me start with the relocation and how it's worked. Well, the concept come about because you have a split between the compiler and the linker. And the relocation scheme is simply provide a mean to pass some information from the compiler to the linker. And the way this is done is that during the compile time, because it doesn't know, let's say, an address of a global pointer, it simply emits a tag such that it allows the linker to resolve that address for the final executable output. Here is an example of that. I have a global variable called global symbol, and then I have a main. Now, if you actually compile that and take a look at the .o file, you will see that the RISC-V compiler generates two tags, which is that R_RISC-V, a HI20, and an RISC-V relax. And this is that special tag that I mentioned that the compiler generates, so the linker can use. With this, during the link time, now, because at the final linking, you know where your global variable is located, that emit tag will get dropped and resolved with the appropriate address itself, as you can see there, which is from there. And that HI20, that simply indicate the high sign bit of the address. So what is the linker relaxation? Well, it's a way to optimize the program at link time instead of at compile time, which makes more sense because that's when you actually know where the rest of your code are. So in this case, I have an example where called c.c, test.c. I have a function called func that simply take the argument and return +1 to that. And a start function that simply called that function. So if you actually compile that file and take a look at the .o, you will see that it has the compiler put this in, and then the compiler emit the tag, and during the linking part, it then resolve it and actually use a jump instruction. You might think, well, okay, what's so special about that? But the benefit actually comes from the fact that, for example, the RISC-V ISA itself, there are two conditional or unconditional control instructions available, namely the JALR and the JAL, where the JAL allow you to jump to an absolute address, where on the other hand, a JAL itself, it only allows you to jump to a PC relative offset. So in the example that you just saw then, during the link time itself, because the linker knows that the offset between these are actually close and within the 22-bit, now instead of using two instructions, now it simply just use a single jump instruction, which is, in a sense, it's improved the performance because you go from a one instruction to a two instruction two instructions to one instruction. Now, how does multi-lib work in RISC-V? Well, let's start with what is multi-lib. It's a mean to handle multiple sets of system library, like in the case where you have 32-bit application in a 64-bit architecture. So what multi-lib gives you is mixing, for example, between soft floating point library and hard float, a mix between soft float and hard float system. And this allows you to build a single compiler that targets any RISC-V system. And because the RISC-V ISA is modular, it allowed the multi-lib implementation to be much cleaner because all the known naming scheme is already detailed in the ISA target. A standard set of ABI, since it's already known for RISC-V, like in the case of a C-type, either an ILP32 or an LP64. On the other hand, another one would be the floating point register, which either provide none, single, or double. So the way in RISC-V, we were able to actually produce this multi-lib by using a script. And if you're interested, you can take a look at that blog, which detail on how you go about resolving that. And here's a snippet or example of that particular script that we use to derive the multi-lib. And basically, all it is simply walk through all the possible ABI, and then for each of that ABI, it then walks through the possible ISA along with the extension to figure out what is the combination between the ISA and the ABI for you to use which particular library. For the embedded toolchain, these are the possible lists that was possible. On the other hand, for Linux, this is the list. So this is what we mean by it's nice and clean, and it's already well known within the ISA itself. Now, so jumping away from the GNU-based toolchain, for RISC-V support, in addition to what was done for the GNU toolchain, there has also been work done in the LLVM toolchain as well, where the compiler and the assembler are now support RISC-V and has been upstream in experimental mode as of 8.0. And with the intention that non-experimental support plan for 9.0. What exactly does this mean? It means that they were able to compile and run through the GCC torture test for the RV32, the RV32IM, and the RV32 floating point with the compressed instruction. Also, and similarly, for the 64, they were able to pass the torture suite for the RV64I for the different optimization flag. At the machine code layer itself, they're now able to support the following ISA. Now, with RISC-V, due to the lack of availability of RISC-V hardware itself, the need of a virtual machine emulating a RISC-V become quite important. And as such, there was work done in the QEMU as well in order to support RISC-V. And that also has now been upstream and is available for download. I would encourage everyone to go and actually try it, because since it's a virtual machine emulation, it's pretty much free and easy to use. Now, another tool which is sort of needed in the embedded space is this on-chip debugger itself, which provides the ability to connect to embedded target for either debugging or running program. Although it hasn't been upstreamed yet, the code is available at the RISC-V GitHub repository itself. And of course, the work for supporting the Linux kernel, RISC-V in Linux kernel, that too has also been upstream since late 2017. And now, with the fact that it is already upstream, it is well supported with over 340 commits related to RISC-V alone went in. And it was demonstrated that you can actually boot a Linux kernel on a QEMU. So I'm going to jump slightly to the embedded area, because in the embedded space, the embedded ecosystem seems to progress much faster in that now there are both commercial and open source tools become available to support both commercial and open source tools become available. Similarly, there has been other work done for the OS as well, but I will get into that a bit later. And as you can see here, now there are over 10 different corporations supporting RISC-V. One of which is the Loaderbyte. They have already supported RISC-V for over a year already, providing the 32, trace 32 for silicon bring-up and debug. They support both the RV32 and RV64 core with SiFive IP, as well as multi-core and heterogeneous multi-core. They also collaborate with Ultrasoft to provide the debug, tracing, and logic analyzer tool as well. Similarly, Sega has also support RISC-V for over a year already, which they provide the Xilinx probe, as well as the embedded IDE. They too support SiFive IP, in particular the RV32, RV64, as well as the multi-core. They also provide the real-time trace with high-speed communication with the host debugger itself. And one of the well-known vendor that recently supported RISC-V is the IAI itself. And they are well known for their proprietary compiler, which provide both code density as well as performance. In terms of the embedded OS, FreeRTOS, which pretty much the de facto OS for small and low-power device, along with the Amazon FreeRTOS software library, has now support a number of RISC-V targets, things like the QEMU emulation of the Hi-Fi 1 or the Open ISA Vega board, and the N-Micro creative board. All that has been support since early this year through the work of Richard Berry himself. SiFive is currently in the process of porting the FreeRTOS kernel onto its open source Freedom Metal library to support all of its SiFive devices. Zephyr, which is another embedded OS, and it is open source, and it is known for the well-defined development cycle, as well as performance, scalable, and strong software stack. They too also support the Hi5 RISC-V in their latest LTS release as well. And they also demonstrate that Zephyr, along with RISC-V core, can be used as a real product, as in the case of N-micro batch. One great thing about Zephyr is that their SDK, which allowed anyone to use it relatively easy. And the benefit there is that it actually comes with the RISC-V toolchain, so you don't need to build the compiler yourself, all the necessary toolchain yourself. How do you go about getting started with a Zephyr? Let's say on a QEMU. Well, by simply just download one of their SDK, which has support for Linux, Mac OS, as well as Windows. And once you download that, you can start building, but first grab the source by perform a git clone from their GitHub repository itself. Then simply just cd into the Zephyr directory, source one of their included environmental script, pick an example, and then run cmake with QEMU as the board target itself. And then simply just run type make, which go and build and produce an ELF binary. And to run it on QEMU, just simply type run. The RISC-V Foundation also published a getting start for this as well, and I provide the link here. Now, in the bare metal space itself, SiFive provide an open source bare metal software stack, which is anyone can basically go and download or clone, I should say, and also participate in the development as well. And they provide this through Freedom ESDK, which is a development kit with a command line environment that has a number of examples and utilities that allow you to build and run things like for a QEMU target or to run on an FPGA board or one of their development board itself. Similarly, the Freedom Metal, which is an open source driver that provide both RISC-V CPU feature as well as SiFive specific peripheral, is also available. If you prefer a more GUI-based, SiFive also have available the Freedom Studio that you can basically download for free and try it out. It is support for Windows, Mac OS, or Linux. It is available at sifive.com. So I'm going to simply run through how you can use the Freedom Studio. And because the Freedom Studio built on top of the Eclipse plugin itself, the process of going to of creating a project workspace pretty much like any other Eclipse-based IDE, where you simply, let's say in this case for QEMU, you can simply go File, New, it's a C project, and then choose the Freedom E SDK. project. And once you're there, now you have an option to select what target that you want to build your application for. In this case, I happen to select a QEMU, and then I pick a simple example as in hello, which print out a hello world. And there it is. On the other hand, if you do want to use the Freedom Studio with an FPGA board, then just like last time, the only difference now is that you get to choose a different target with the FPGA, and also you can choose the same example or a different one. And then click Finish. But one great thing with Freedom Studio is that it also provides you the ability to flush your FPGA as well, without the need of using Xilinx Bravado program. And this was done using the open source HC31-T2 Pro from Xilinx. And debugging through the Freedom Studio is just like any other IDE clip. You can set breakpoint. You can look at your program variable. You can inspect the memory content and export it if you choose to, as well as you can go down and actually take a look at the core register. It also can launch a terminal console as well. And if you want to see for your C program what set of RISC-V assembler look like, it also has a window tab for that. So that's the GUI part. And because the Freedom Studio is built on top Freedom ESDK itself, which is a command line environment, you can easily get access to that by simply cloning from the SiFive GitHub. However, you do require a number of packages to be downloaded, namely the GNU make for you to build, Git for you to do the Git clone, and of course the embedded toolchain itself. Since the Freedom ESDK, it's the command line, and you Git clone it, it does not come with that. Fortunately, SiFive do pre-build this toolchain. It is available at sifive.com for you to download. Or if you prefer, you can go and actually to the GNU website and actually build the toolchain yourself. And of course, if you want to run it on a QEMU or run it with a physical board, you either need to download the QEMU or the Open OCD, or the Sega Xilinx as well, in case you want to use the Xilinx connection. And to use the Freedom ESDK, once you have all those tools downloaded already, it just requires one single environment to be set, which is the RISC_path that you need to point to where the tool chain is. Once done, you can simply build a program or an example, like in this case, by simply type make program, specify what program you want to build and what target. So in this case, I'm building hello for a QEMU target. To run that on QEMU, simply type make simulate and what program you want to run and your target itself. There are many other examples that you can choose. I just happen to choose a simple one here. So how does Freedom ESDK sort of use the Freedom metal and how it actually ties together? Well, so remember when you do a make and you specify the target, associated with that target, there is a description for that particular target or hardware. And that is typically one way of representing that is through a DTS. And a DTS file has already been used within the Linux community. It has a spec, and I guess is well adopted in the community already. So what FreedomE SDK does is simply take that DTS file, which is a description of the hardware, and use that to build a library, a bare metal library specific for that target, such that when you then build with your application, it allows to link to the appropriate target that will access the appropriate hardware. So just in case, here is a sample of what that DTS file looks like. And as I indicate earlier on, is that the DTS is nothing more than a description of the hardware devices. And in it, it has nodes. Like in this particular case, one of the nodes is a CPU, and you could have multiple CPU. Oh, this didn't turn out well, did it? Because of the porting between Google Doc and Microsoft PowerPoint, I guess. But basically, a DTS file is nothing more than a data structure representing all the different components for that particular board. So the way Freedom Studio does it is simply pass that DTS file into a bunch of BSP files that it can use that simply tailor or target a particular hardware. So here, what I'm showing on the right-hand side is a sample of that DTS file, and on the left-hand side is a sample of the DTS file, and on the right-hand side is what the FreedomE SDK generates as an intermediate file known as the BSP file. And what this does is that from that open source library that's available in Freedom Metal now, in there, it has no knowledge of a particular hardware at all. It simply references a particular function that would be described by a BSP file associated with that target. And this allows the Freedom Metal library to be very much portable, because you no longer now have any hard code reference or specific to a particular hardware, which is important, especially for RISC-V with custom SoC and so forth. So here is an example of a program that one might write. And one great thing with the Freedom Metal, since it is portable already, that is, it doesn't have any direct reference to a particular hardware, is that that extension also come out onto its API that can be used by the application as well. So I'm not sure if you can, oh yeah. So in this particular case, as you can see in this example, the first part is that I want to have an ability to have access to an LED and then turn it on. So as you can see in this example, there's no notion that, okay, I need to know what is the address of that. But because all that is hidden by the Freedom Metal it is already, from your application perspective, you can simply say, give me a handle to a device known as an LED. But how does that work? Remember the DTS file, which describes the hardware, and one of the components or one of the nodes it has is on LED. In there, as you can see, it has a label, which is to say that it is an LED. And it also have a reference to another node, which is the GPIO, where it contains the address for you to turn on and turn off the LED. Right? So as you can see here, it will make the application very portable. And this is one of the reasons that Freedom eSDK, you can easily build for multiple targets without changing the actual application itself. And here is another example in regard to the timer interrupt as well. In this particular example, it simply wants to have access to the timer controller interrupt. Now, you're probably already aware is that with RISC-V, there's 2 local interrupt controller available. One is known as a clint, and the other one is a click. Now, from an application perspective, it shouldn't need to know whether a particular hardware is a clint or a click. I mean, you could write one to have that knowledge as well, but that would imply that if you want to compile that particular code for a board that doesn't have a click, then you have to change your code. Here, it simply indicates that, okay, give me a handle to an interrupt, to a timer interrupt controller. So how does this work? Well, by doing so, when you compile this particular program with a target that you specify that has a clean itself, because the BSP dictate and have all the information associated with the clean, a library for that particular hardware has been generated for that particular target already. So that this particular application, when you build for that target, which has a clean, will use that particular library. On the other hand, the same program now, without changing anything, can be built again, now this time, to a target that actually have a click. So that's pretty much where the embedded space is. But now I'm going to jump down a bit into Linux. And as you're probably already aware, after having RISC-V support in the Linux kernel already, there has been 2 RISC-V Linux projects that has been working on. The first being the Fedora project itself. And much of this effort is from David, where he has now able to basically port 20% of the Fedora packages to support RISC-V. He also have set up a build farm that simply just every night pre-build the Fedora image for QEMU. Unfortunately, there's no signed RPM yet. Neither is there images for you to simply boot on a Fedora workstation or a server. But a lot of effort has gone in. I encourage you to go and check it out with the link I provided here. And you can also download one of the pre-built image itself. It is self-hosting image, so you can actually install it on the QEMU. The other Linux distro that supports RISC-V is the Debian distro. It actually progressed a bit further, where over 84% of the Debian packages has been ported to support RISC-V. Of course, we have demonstrated, you all probably have seen the demo where you have Quake running on Hi-Fi Unleashed. And at the moment, it too also doesn't have a Debian installer. However, you can go about create a boot image by following the instruction at SiFive Freedom U SDK site. or check out the Debian RISC-V link itself. So how does the Linux boot flow work? Well, this is my attempt of representing that, but I can understand this is a bit messy. Here's probably easier to follow. Basically, the boot flow for our Freedom Unleashed sort of break up into a number of stages, where the zero stage, which is in a mass ROM itself that's been baked onto the chip. It contains the reset vector for all the hard. Okay, it simply stay there. When on power on, it look at the dip switch and load the appropriate partition based on the selection of the dip switch for where or which SPI or flash that it can sort of boot onto, which is the first bootloader. So in the SPI flash, what it does is simply load the images from flash onto an L2 limb, which is a local, loosely integrated memory. There, it initiates the DRAM, the Ethernet, and the clock controller, and then load a bootloader from an SD, because it's a SPI flash. And that bootloader is nothing more than the BBL itself. So in the BBL, which is run in machine mode. It filters out the device tree for the Linux and disable the hard autocore that does not need to run Linux. It also contains trap handle for unimplemented instruction, as well as RD time, which trap to the clean or on a floating point system and set up a floating point on the system without a hardware floating point. It also contains the SBI implementation, which say that resident during Linux and handle the remote fencing as well as setting up an IPI with the clean. It has helper function for early debug console if it need to. And then once done, it simply load the flat binary Linux image. In the Linux early boot itself, typically a Linux early boot expects the following. The system to be in the following state, in that it expects that the A0 register contains the hard ID, a unique hard ID, I should say, and also the A1 contains a pointer to a device tree, which is a binary flattened device tree. The memory is identity map, and the kernel elf image has also been loaded correctly. It also handles impedance mismatch between the RISC-V spec as well and the Linux and what the Linux expects, and then perform a hard load tree where it simply just pick one of the hard to boot, while the rest can simply just spin until they're allowed to proceed. After that, it simply goes through the normal standard Linux early boot process, where a linear mapping of all the physical memory is set up with page offset, and the paging structure are initialized and then used. It also, the C runtime is also set up there, which include setting up the stack and the global pointer, And a spin-only trap vector was then set up just in case during the boot process there is some sort of failure. Once done, it simply jump to the start kernel to enter the standard Linux boot process. In there, it simply unconditionally enabled the early print console using the SPI. And then when the kernel command line is passed and the early architecture-specific options are dealt with, user can only control the amount of physical memory that can actually be used by Linux. The device tree memory map is passed in order to find the kernel image memory block, which is marked as reserved. Then the rest of device tree memory is released to the kernel for allocation. The memory management subsystem is then initialized. However, only the zone normal is supported at the moment. Any other hard in the system at this point will be brought up. The processor ISA is then read from the device tree, which is used to fill out the hardware cap field in the ELF. And this allows the user program to determine what hardware they can execute on, or however, homogeneous ISA is assumed here. And then it simply just returns back to the upstream kernel code. That's pretty much the RISC-V Linux boot flow. So to sum up, I would say, get started. Either grab yourself one of the physical boards available today, like the Hi-Fi one, which is more targeted for embedded development. It is available on Crowd Supply, or a Hi-Fi Unleash, also available for from Crowd Supply, if you're more interested with Linux itself. Or you can simply just download the latest QEMU and try it out there first. If you need any IDE or command line environment, both, they are available at sifi.com or at the SiFive GitHub. You are welcome and encouraged to try it out. If you have any question, simply send an email to softwaredev@groups.risc5.org, or simply get on to the IRC free node with the hashtag RISC-V. I think that's it. Thank you.
Time for any questions?
Hello. I have a question for each of the panelists.
Okay.
The first question is there something similar to the Symesis framework that exists for ARM, meaning it offers all of the APIs for initializing the core, or simply writing onto the CSRs, et cetera? And my second question is if the SiFive speaker could elaborate on the license for using Freedom Studio and Freedom Metal for commercial purposes.
Sure. The Freedom ESDK and the Freedom Metal, they are open source, and you can use it. We encourage you to contribute to it as well. We have made it public for over a year already. In regard to the Freedom Studio, it is available for download, but I don't think we're at a point that we can actually release the source code yet. But for the Freedom E SDK, which the Freedom Studio sort of built on top on, that's also available, and you're welcome to take a look at how it actually put together.
So I have a question that might be more to you. First is about the microarchitecture. What kind of model do you use here? I'm kind of thinking about ARM, where they wanted to control microarchitecture, and also about kind of licensing. So what if somebody wants to use your RISC-V and change the instruction set or whatever? So what's your approach on this one?
Well, for RISC-V, there is no blessed microarchitecture. As long as you follow the ISA interface, you can do whatever you want in the microarchitecture. So it's up to you. On the, sorry, what was the second part of your question? Oh, with the extension, yeah, it was designed for extensions. So like I went through in my talk, there's a standard part of the ISA, which all the standard tools drive. There's space left to do whatever you want over on the side. And the idea is you should be able to use a standard tooling that drives the standard extensions to do most of the stuff you want to do. And then over here, you can add your custom stuff, and that's fine. So everybody gets an architecture license for RISC-V. You can do whatever you want there. There's no... If you change the base ISA, then you're not using RISC-V, you're using something else. And that's great, you can go and do that, but you won't have the support of the standard software ecosystem, which is really the most important part of RISC-V.
Hi, Jeff Smith, Citadel. I have a question about the original architecture, or sorry, the original instruction set design, so maybe 10 years late question. But in as much as you've gone down to like the smallest set possible, and it doesn't look like you have like a bunch of like condition bit flags set by various instructions. So if you have something like signed integer overflow, that you'd be doing tests on the operands and stuff, as opposed to just catching a bunch of flags later. Did you guys consider doing things like trap bits or trap values for signed integers?
Yeah, we did, and decided not to do them. Bunch of reasons. One is a lot of the code, smallest machines won't run software that expects that to be there, for one thing. Also, when we have a J extension working group, which is specifically around dynamically translated languages and languages that can deal with, that want to deal with these things, they have iterated several times on what they want, having looked at, so for example, condition codes and explicit traps are really bad because trap vectors are shared by many parts of the code, so having traps isn't seen to be good. Having condition code flags is bad for the microarchitecture, nobody likes those. So they're still thinking about what they really want. So in these cases where nobody really is sure, or the ideas people have tried previously have flaws, we like to have people keep looking at it, and they are continuing to look at how to handle that particular case of integer overflow. It's actually not that many instructions to do it. In the manual, we go over the little sequences you need. For a lot of common cases, it's just one extra instruction you need to catch an overflow. Other cases, maybe 2 or 3, but people are looking at it and thinking about it, and there's not a simple answer. The previous solutions have problems, so.
It's a known big problem, but it's kind of a chicken and egg problem where languages don't have features added because no hardware does it, right yet. So people are just waiting on the other sides to kind of come together. And I mean, at some point, maybe like the next architecture will come out to try to address some of these things. We have like the last thing wasn't great enough. We'll need one more just to do whatever. And this is one of the things that kind of caught my eye is just.
No, we thought long and hard about it and continue to think long and hard about it.
Okay, thank you.
So I think there is a lot of competition between the general computing processors and the AI processor and NPU, so forth. Is there any intention for the RISC-V Foundation to push specialized instruction for the new emerging applications such as an AI?
So the vector instruction set is being designed as a pretty general SIMD, 1D SIMD instruction set, but there's a lot of interest. Already in there is support for data types and things that are applicable with a lot of AI/ML workloads, and I think over time you'll see some more extensions that will be more targeted at AI/ML within the vector framework. So this final hour of the tutorial, we have 2 half-hour sections talking about 2 different families of open source RISC-V cores. So first we have a group from UC Berkeley talking about their open source cores. The presenters there are going to be Howie Mao and Jerry Zhao, who are graduate students at UC Berkeley. So I'll let them get ahead and tell you what they've been up to.
Clicker. Oh, there you go. Thank you. Hello, everybody. I'm Howie, and today I'm going to be talking about generating rocket and boom SoCs using rocket chip. So what? Okay. What? Wait. Oh, okay. So what is rocket chip? Rocket chip is a highly parameterizable SoC generator that you can use to generate RISC-V based SoCs with things like a rocket core, your own custom core, custom co-processors, or custom Encore IP. It can also be used as a library of reusable SoC components that provide things like memory protocol converters, arbiters, crossbar generators, clock crossings, and asynchronous queues. It's also the largest open source Chisel code base, and we use the power of Chisel and Scala to build more complex generator features. And Rockchip was developed initially at Berkeley, but it's now maintained by a large group under the umbrella of Chips Alliance, and so active development is now being done both at SiFive and at Berkeley. So Rockchip can be used to generate a variety of SoCs in industry. For instance, the SiFive has used Rockchip to generate the E-series and U-series SoCs, such as this Freedom E310 SoC, an embedded SoC. And then at Berkeley, we've used Rockchip to generate our own academic test chips, like Hurricane 1, as you see here, and also Hurricane 2 and Eagle. And you can see some of not entirely exhaustive timeline of the chips that we've taped out at Berkeley here. And so Rockchip is built with Chisel, as I said previously, and Chisel is a hardware construction DSL built on top of Scala. And it allows description of RTO in a more programmable way, using object-oriented programming and functional programming paradigms. However, it is not a Scala to Gates or HOS in Scala language. So we use the features of Scala to build complex parameterized generators. For example, here you can see a pipeline that takes in n 32-bit integers and adds them together over log n stages to produce a 32-bit output. And most importantly, Rockchip is fully open source, so you can find it on GitHub under Chips Alliance. And you can also find some of the projects that we built on top of Rockchip, like Quadcha and Boom, and also the FireSim simulation platform, which also uses Rockchip. So here's the structure of a typical Rockchip SoC. First, of course, we have the tiles, which is the unit of replication for a core. So each tile has a CPU, an L1 I-cache, and D-cache, and a page-table walker. And the L1 is refilled from these shared L2 cache banks, which handle the coherence across cores. And they handle the coherence across cores and are refilled from an off-chip DRAM, which is compatible with AXI4. And then we have a front bus, and this is our front-end bus, I guess. And this is how you connect DMA devices, either from off-chip or on-chip. And this means that DMA devices can write coherently into the memory system. We have a coreplex bus, and this is for connecting core complex devices like the boot ROM, the interrupt controller, and debug unit. You have a periphery bus to connect peripheral devices. And finally, you have a system bus that ties everything together. It's a bus for connecting other buses. So first, let's talk a bit more about the Rocket in-order core. This is the first open source RISC-V CPU ever made. It's an in-order single issue RV64 core, and it supports many of the standard ISA extensions that Krste talked about earlier this afternoon, such as the floating point unit, compressed instructions, physical memory protection, supervisor ISA, and virtual memory. And because it has support for these extensions, it can boot Linux. And currently we can successfully boot Build Root and Fedora Linux. Rocket also supports the rocket chip coprocessor interface, also known as ROC, and this is how we build our research accelerators like Quacha. And of course, it has a separate L1 I cache as a D caches, and the D cache can be configured as a data scratchpad for embedded applications. So to connect the tiles to the rest of the system, we have a protocol called TileLink. And this is a protocol designed at SiFive. It is a memory and cache protocol. It has a configurable data width and multi-beat transactions. It has 3 different protocol levels with increasing complexity. First, we have the uncached lightweight protocol, which are the generic reads and writes. Then we have an uncached heavyweight protocol, which adds support for atomic operations and prefetch hints. And finally, we have the cache protocol, which adds supports for probes and releases, which allows the memory to be kept coherent across multiple caches. And Rocketship provides a library of reusable TileLink widgets that can do things like convert to and from other memory protocols, such as AXI4, convert among the 3 different levels of TileLink, adapt the data width and number of beats between different TileLink ports, and generate TileLink crossbars, such as the buses that you saw earlier. And so using TileLink, we can add these core complex devices to our SoC, and these are necessary to actually run programs on the CPU. So of course, first we have the boot ROM, which contains the zero-stage bootloader, which is the first set of instructions to run when the chip is powered up. And this boot ROM also supports the device tree, which Linux uses to determine what other devices are connected to this SoC. And then we have an interrupt controller called a PLIC. We have core local interrupts, such as software interrupts and timer interrupts. And then there's a debug unit, which can be used to load more instructions onto the CPU into memory, or read data back from memory. And this can be accessed through a custom DMI protocol or through a standard JTAG protocol. So we also have the L2 cache and memory system. There's a multi-bank shared L2 cache, which is developed as a SiFive. It's fully coherent. You can configure the size, associativity, number of banks, and it has support for atomic operations as well. And then if you don't want to use an L2 cache because you don't want to use all these SRAM, you can use a non-caching L2 broadcast hub, which still provides coherence. It can still do probes and releases to the L1s, but it does not cache any data itself. And if you want to reduce the resources even more, you can configure it to use a bufferless design. And then, of course, whether you're using the L2 cache or broadcast hub, you can refill the memory from a multi-channel memory system, which converts TileLink to AXI4 from compatible DRAM controllers. So, right, so here I'll turn it off to Jerry to talk about Boom.
Thanks, Howie.
Troubleshooting.
Yeah, the other core option,
fixing all the, but you leave it untouched.
Machine. So while Rocket, the default Rocket chip core, is a single-issue in-order core, Boom is meant to be a high-performance superscalar out-of-order core in this ecosystem. So like Rocket, we're also fully integrated in the Rocket chip ecosystem. We're also open source. We're also a parameterized chisel generator. And what this means is that Boom does not refer specifically to one instantiation of an out-of-order core. Rather, it refers to a generator which can stamp out various cores across a design space of out-of-order cores. And Boom has been taped out. If you were at Hot Chips last year, you would have seen Krste, a graduate student at Berkeley, and the original author of Boom, who led the first Boom tape out as the Broom chip. And like Rocket, Boom also supports the full RISC-V 64-bit ISA with the standard extensions necessary to boot Linux. So I can take an off-the-shelf Fedora image and boot it on my Boom-based SoC, no problems, and run real applications and real workloads as well. We're also a drop-in replacement for Rocket, so fully compatible with the Rocket chip ecosystem. So before I dive into the microarchitecture of Boom, I'd like to reiterate that since Boom is a parameterized generator, we're not one specific configuration, even though I'm going to go over one specific configuration today. So in this block diagram, you'll see that there's a lot of asterisks present, and each asterisk indicates this is some parameter or value of the core that can be configured at elaboration time. So starting with the front end, we can see that Boom has a pretty standard superscalar front end. We try to fetch and decode multiple instructions per cycle. And we also have several branch prediction structures to ensure good utilization of our fetch bandwidth. And this is fairly typical of most modern high-performance processor designs. So moving on to execute, after instructions are decoded, they enter the execute stage. They are renamed to use physical registers in the rename stage. They get allocated to the slot in the reorder buffer. And then they get dispatched to our distributed scheduler. We have 3 separate issue queues, one each for floating point, integer, and memory type operations. When the operands to an instruction are available, the instruction issues. It reads its operands through the bypass network or through the physical register files. And then it goes down to execute in these execution units. And the layout and number of these execution units is also all configurable. So here you can see we've configured a 7-wide machine with 3-wide integer, 2-wide floating point, and 2-wide memory. So specifically on memory, taking a look at the memory subsystem, Boom can generate up to 2 load addresses and store addresses per cycle. The load addresses go into the load queues. The store addresses go into the store buffer. We can forward from the store buffer to the load queue at 16 bytes per cycle, so pretty standard design. And as for accessing the L1 data cache, it can fulfill 2 independent loads per cycle or 1 store. So this is 16 bytes per cycle load or 8 bytes per cycle store. And zooming out, we can see that the L1 data cache and L1 instruction cache are connected to the external L2, which Howie mentioned earlier. And this is the mega configuration of the Boom core. So sort of the reason why we're developing Boom is we're trying to develop a platform for people to do open source research on the design and the behavior of out-of-order cores. So if we compare Boom to other modern high-performance cores, we can see that structurally and behaviorally, Boom demonstrates many of the same behaviors and exhibits many of the same structures. And so an example of how this might be useful for research is, security researchers who have been implementing Spectre mitigations in Gem 5 can now implement a real RTL implementation of their proposed mitigation in Boom and get real empirical power performance area and, of course, security numbers for the proposed implication. So this is just one example of how we hope Boom will be very productive for research, and we're already seeing some interest from the community in this regard. So comparing Boom and Rocket to the other commercial cores out there, we can see that performance-wise, they're roughly comparable to similar cores, with the primary difference being, of course, we run the full 64-bit RISC-V ISA with all the standard extensions. And I also like to point out that you can see that the source code, the size of the source code for Boom and Rocket tend to be fairly concise. And this is an artifact of how they are expressed as chisel generators rather than as static descriptions of hardware. So the concision of their source code makes it really productive to do design space exploration or to implement some custom block or modify the core. So it's really productive for research. All right, so now I'm done talking about the cores. I want to talk about another level of customization available in the Rocket Chip ecosystem, which is the ability to add your custom accelerator through the ROC, or the Rocket Chip coprocessor interface. So as Krste mentioned earlier, the RISC-V ISA leaves opcodes available for implementers to implement their custom extensions on. And so the ROC interface, what this enables is the implementer to implement their custom extension and then implement a custom block which will execute instructions for that extension, and then place that block within the full Rocket Chip ecosystem and run it with a standard unmodified Boom Rocket tile. So what we see here is this interface allows you to place a decoupled ROC accelerator within the tile. The accelerator will receive your custom instructions from the unmodified Boom or Rocket core, and it can optionally write back into physical registers of the core, access the page table walker, read and write from the L1 data cache, or even go straight up to system memory to the system bus if necessary. And so this is a very versatile interface, and it's been very productive for our research. So here's an example of some of the accelerators that students at Berkeley have developed using this interface. And you can see we've developed a variety of accelerators across a variety of different applications: vector accelerators, memcopy, machine learning, garbage collection. So this has been very useful for our research. All right, so at this point, we sort of described the component, the library of generators available in the Rocket Chip ecosystem. So now the question is, all right, we have this bag of generators. How do we integrate them together, configure them to produce a full SoC? Well, being implemented in Chisel and Scala, Rocket Chip incorporates this very powerful configuration system, which really simplifies this task of configuring and integrating an SoC to just mixing in different configurations, different modules on top of a base configuration. So to illustrate how this works, I'm going to walk through the design of a simple semi-custom SoC in the Rocket Chip system. So we specify we want to create a new class, myCustomConfig, and it's going to extend off. We're going to start by extending Rocket Chip's base config. The first thing we do is we want to specify what our top-level module is. So we're going to say we want a normal boom rocket top. This top is going to have a system bus, a memory bus, some of the other peripherals, how we mentioned, as well as this also specifies what IOs the top-level module has. All right, so we have our top. What's the next step? Let's stamp out 3 boom cores. We want a 3-core system. Each core will be an out-of-order boom. So we just use this mix-in. We say we want 3 boom cores, and it will automatically stamp out these 3 boom tiles for us. But let's say for my design point, I want to use specifically a 3-wide boom. I can just configure that by adding another mix-in. With large booms, we'll reconfigure all of these booms to be 3-wide. And we can keep going, right? So I want an L2, 1 megabyte large. So I use the with inclusive cache mix-in, specify my L2 capacity as 1 megabyte, done. Continuing, all right, let's say my SoC, I want to run scientific computing or data parallel applications on it. So I want some sort of vector accelerator. Well, I have the Hwacha vector accelerator. I use this mix-in. Now every tile has a ROC Hwacha accelerator attached to it. So every tile can now execute Hwacha vector instructions. And we've now specialized every tile for data parallel applications. All right, so we should finish up this top now. Let's add a boot ROM. Let's add some GPIOs. And at this point, the top's done. But we still want to be able to simulate our SoC in software. So we should finish up the harness as well. So let's add in a simulated block device for disk images. So this sits in the test harness outside the top. And also a simulated external DRAM, 2 gigabytes in capacity, to model the imaginary system I'm building. So at this point, we have a full SoC. We could take this, we could generate the Verilog for it, and I'll show you in a couple slides down how to take this through software simulation, FPGA simulation, or even tape it out. But I also really want to emphasize how powerful this rocket ship configuration system is and how easy it makes the task of customizing or integrating different blocks into your SoC. So I'm just going to go through a couple more degrees of freedom which this configuration system exposes. So for one, there's no reason why we have to have a homogeneous system. Let's build a heterogeneous core. Make one of the tiles use a rocket in-order core instead. We also don't need to have homogeneous accelerators. Let's have heterogeneous accelerators. So one core will get a Hwacha vector accelerator, another core gets a SHA-3 accelerator, another core gets a machine learning convolutional neural network accelerator. We don't even need all the cores to run the same ISA. Let's make the rocket core run 32-bit RISC-V. We can add JTAG, more peripherals for debugging. We can even do something like reorder the numbering of the tiles just by specifying one line, one mix-in. And finally, we can also put the tile, we can add clock crossings between the tiles and the top. So now each tile is on its own clock domain. So this is more realistic of a system you might actually build. Right? So hopefully by now you get the point that this rocket ship configuration system is an extremely powerful system for configuring your ISA and reducing the problem of integration into just specifying the mix-ins you want. And this is really all possible because of the rocket ship philosophy of instead of building static descriptions of hardware, we build generators that are parameterized to stamp out parts and automatically wire things together the way we want them to. All right, so we have our config. Now what's the first thing we do with it? We do software simulation. We start with a chisel. We start with a config we define in the Scala file. And we run chisel elaboration on this chisel. And what do we get? Well, we get behavioral Verilog for the top, the test harness, and the memories in the design. And you can throw all this at your software simulator platform, like VCS or Verilator, and get your simulator out of it. So this is pretty standard stuff. What about FPGA simulation? Well, the problem here is that we usually can't just take the same behavioral top-level Verilog and throw it at our FPGA simulation platform. And it's probably not well optimized. It might not be SACO accurate. And we also usually need to generate some host-side drivers to run our simulation as well. Well, we can configure Rocket Ship to do that as well. So this time when it elaborates, it'll give us transformed top-level Verilog and also configuration information for any host-side drivers that are running our simulation. And then we can throw this to our FPGA simulation flow, like FireSim or SiFive's FPGA shells, and get an FPGA bitstream out of it. All right, so you've done software sim, FPGA sim. Now you want to tape out your chip. What do? Well, again, you go back. You start with the same chisel generators. You start with the same configuration you declared. Now, so one of the challenges in tape-out is that you can't give the tools behavioral Verilog for your memories. You need to give them your memories mapped to the SRAM macros available for that technology. And we can automate this. We can write passes into Rocket Ship that will automatically convert the memories we specify in our design to the SRAM macros which we have available to us in that technology. And this entire process can be automated away within the Rocket Ship generator. So we have our SRAM macros. We have our top-level Verilog. Again, we throw it through the tools through the VLSI flow, and we get a GDS out of it. So one more thing, what good is an SoC without software, right? So typically software developers don't really care about the Verilog implementation of the chip. What they care about is stuff like, what ISA does it run? How many cores does it have? What is the memory map? What is the device tree? And again, we can get Rocketchip to automatically generate all this collateral for us and pass this either to a developer or some sort of automated build system in order to get our software out. So taking a step back, looking at the big picture, we can see that the power of Rocketchip is really, it provides this unified design flow going from your chisel source, so your one source of RTL, so to speak, and it can generate all of these different artifacts which you might need for different use cases, whether it's software simulation, FPGA simulation, tape out, or writing code for that SoC. And so sort of as evidence for this, I want to go through all of the different ways how this Rocketchip ecosystem has benefited research we've done at Berkeley. So as Howie mentioned earlier, the numerous academic tape-outs done at Berkeley over the past few years have all been built on the Rocketchip platform. As we also mentioned, the numerous research into accelerators, designing and evaluating accelerators within the full system setting has all been built on the Rocketchip platform as well. Rocketchip's also driven out-of-order core design with the Boom project, FPGA accelerated simulation technologies with the FireSim and Midas projects, debugging methodologies, power modeling, and security as well. So here are some of the active projects currently going on which leverage Rocketchip or are improving the Rocketchip ecosystem. So at Berkeley, we are continuing to develop more open source components for the Rocketchip ecosystem. As we finish our research and publish it, we will continuously develop open source repositories, and whether they're generators or utilities that extend Rocketchip, we'll continually open source them and make them available to the community. So another project I want to talk about is Chipyard. So Chipyard is sort of an end-to-end hardware design template for Rocketchip, which we're currently in the process of building. And it's meant to make this task of taking all these different Rocketchip components, integrating them together, and sending them through the different flows, make this as sort of like a one-stop shop to do all of these tasks together. And also FireSim, as we've mentioned, FPGA. Rocketchip is really driving FPGA simulation, debugging, and profiling technologies under this platform. Hammer is a tool for automating VLSI flows. So the dream here is one day you'll be able to specify your Rocketchip config, specify your target technology, and then just type make GDS. And Hammer will automate all the tools, automate all the flows for you, and it's push button from configuration to GDS. So that is sort of the vision for this project. Also Boom, the out-of-order core. In order to make this useful for research, we're continuing to improve its performance, its security, continuously adding more features, thinking about how do we make this for other people who want to look into out-of-order core design. And also Hwacha, the vector accelerator, looking at various types of vector execution. And also on SiFive's end, because they're also working on maintaining Rocketchip, they're currently trying to make Rocketchip closer to the vision of a composable library of various components. And also we are interested in developing more open source educational content for Rocketchip, bringing Rocketchip-based projects into our courses at Berkeley, and of course producing open source tutorial and class content using this system. All right, so that's the end of the talk. I'm gonna leave you with links to some of the repositories we discussed today. So starting off, Rocketchip is the base repository. We also have Chipyard, which is a design template for putting everything together and running Rocketchip SoCs through these flows. If you want to sort of do a hands-on tutorial, taking your custom Rocketchip-based SoC design, taking it through software simulation, FPGA accelerated simulation, and taping it out, at Micro 2019, we're going to be giving a tutorial with FireSim, showing you, doing a hands-on tutorial, showing you how to do this process for a custom design in Rocketchip. And Chipyard is going to be formally released at that time. Right, and here are some of the links to some of the other repositories. And I think we have about 6 minutes for questions now. Thank you very much.
Shrikant from Google, thanks for the excellent presentation. And it's great that you guys are thinking in terms of building this push button flow, but bulk of the effort in designing a chip is to focus on things like performance, which involves tight integration with the technology that you're building and verification, right? Mm-hmm. So how do you ensure that in this flow, like if you design with a particular target in mind, that you will be able to hit timing at like a gigahertz, for example, and it meets the power and other requirements that are necessary for the chip to be deployed successfully?
So for physical design, that's really sort of the purpose of the Hammer project, is to sort of like try to automate that as much as possible, to sort of separate the concerns of the design of the hardware and technology-specific parameters or features, and sort of like devise some automated system, like given this chip I want to tape out, and given the parameters of this technology, figure out how I should place things or route things to meet timing. So that's sort of under the purview of the Hammer project. And the other question was verification. So we mentioned how Rockchip was all based on Chisel. What we didn't mention was that Chisel also, Chisel is a very powerful language, and it emits an intermediate representation of hardware called Fertile. And there's a lot of area between Fertile and Chisel for people to develop various verification techniques. And we have people working on that approach as well. So verifying either the Chisel or somewhere between Chisel and Fertile.
Hi, actually, it's quite a little bit like similar questions, but like especially for the tape outs that you guys did with using Chisel and this architecture, like when you had to close the timing, did you go all the way back to like Chisel, or did you take the Verilog generator from Chisel and then like hand modified on top of it?
They usually go all the way back to the Chisel. We try to avoid hand modifying the emitted Verilog. So what we can do is, instead of hand modifying the emitted Verilog, we can write passes on top of the intermediate representation that Chisel emits. So instead of like hand tweaking something, we can write a pass that does the tweak for us, and that sort of automates that away.
And regarding also like verification, is there any like plan or effort on kind of the concept of like by construction, correct design? Because
right. So I guess that's one of the advantages of Chisel, right? By being a highly productive and concise language for expressing hardware, there's less area. Like if your code is 10 times more concise, there's 10 times less lines for a bug to occur, right? And so that's naturally, I think, kind of good for reducing the amount of bugs in a design.
Thank you.
I might ask one question. Sorry. So you talked about FireSim. Is it specific to the rocket chip simulation on FPGAs, or is it something that you're developing for general purpose and doing this here?
You want to talk about
Yeah, so the idea of FireSim is definitely to have a general purpose hardware simulator, but right now the generators are written in a way mostly to support simulating rocket chip and associated designs.
Take the final question, maybe this side.
Kai from Texas Instruments. I'd like to know some of the details, like just data-wise. If you have already taped multiple of these chips, is there any numbers that you can share, like area, power?
We do have numbers, but not in this presentation.
Running like Drystone, for example.
Yeah, we do have those numbers. They're just not on these slides, and I'll have to look them up for you. But we generally do have those numbers as well.
Which process you use to tape out the chip?
Variety. I think the most recent were TSMC 16.
And rough number of the area?
I'm sorry, I wasn't the one involved in those tape outs.
Okay.
Okay, let's thank the speakers again. Okay, so that was the Berkeley Open Source RISC-V course. Next up, we have Fabian, who's going to tell us about ETH Zurich's line of open source RISC-V course.
Hello, good afternoon, everyone. My name is Fabian. I'm a PhD student at the ETH of Zurich with Professor Luca Benini. I'm a member of the Pulp team, the parallel ultra-low power platform, and this is what I'm here to talk to you about in this last session of the afternoon. So basically, the Pulp project was a project started in 2013 by Luca Benini. It's a collaboration between the University of Bologna in Italy and ETH Zurich. It's grown quite a bit. It's a pretty large team. We have roughly 60 people working on it. Not everyone is working on Pulp directly, but working on side projects or things that are peripheral to this. The key goal behind the Pulp project, which kind of unites all these 60 people, is how do we get the most bang for the energy consumed in a compute system? So this is really what everyone strives for in our group. The good thing when we started out back in 2013 is that we basically started from a clean slate. So there was no need to remain compatible with any legacy system, which we fully leveraged back in the day. So actually, our research originally was not really developing processors at all, but it was developing processors. It was a requirement because we needed good processors for the systems we built for research, and we needed to tweak them. So initially, back in the day, our options were basically either build our own, So also including the software support and the tooling that goes with it. Use a commercial processor with all the licensing issues and collaboration issues that come with that. Or use what is openly available, which back in the day was OpenRISC, which was briefly touched upon earlier in the afternoon. So our first chips until mid-2016 were all OpenRISC cores. We spent quite some time optimizing the cores which were available and improving the microarchitecture. And only at the later stage did we actually move forward to RISC-V because it had a much larger community. There was a lot of momentum surrounding RISC-V. And the transition for us was actually relatively simple. It was basically a new decoder for the processor core that we developed. So as a quick motivation, why we actually want to strive for this ultra energy efficiency for these cores across very wide range of applications is if you consider, for example, an edge computing example where you have a small device, a microprocessor kind of processor there, some Internet of Things application, you usually have things like an image sensor which acquires a picture or an image. This gets processed. You're doing some artificial intelligence, some machine learning. You process this on the device. You push it through a neural network, and then this produces an action for you to take. This could be any kind of control application. Now, this works well, but the problem is that usually you want to go to more and more sophisticated levels in your machine learning applications, and suddenly you run out of compute power, which the microcontroller offers to you. So what we observed, the general trend there then is to actually take the images that were captured and move them into the cloud and do the processing there where you have the huge compute capability of the cloud available, then go back with the action onto the actual IoT edge device and perform the action there. And as you can imagine, there's all these latency and privacy issues that come with that. And not only that, but there's also a cost involved by actually having this huge amount of data being moved from the edge devices into the cloud, processed, and then moved back. Actually, to an extent where we observed that if we can save 95% of the data volume being pushed into the cloud and process this thing on the edge device, there's significant cost reductions to be had. So this is kind of the key challenge in this extreme edge AI case where we want to have AA capabilities below 1 picojoule per operation, which is kind of the microcontroller power envelope usually. But still you need mega to teraops of operation capabilities because you want to crunch really big machine learning models and do sophisticated work. This kind of forces you to go beyond the classic 32, 64-bit floating point formats. So our answer to this basically is the parallel ultra-low power platform, which originated, as I said, back in 2013. Now, the key ingredient here is that we don't want to waste energy by pushing our silicon devices into strong inversion. What we do instead is we lower the supply voltage to move them closer into this regime, which is called near-threshold computing. And what happens when you reduce the supply voltage, your dynamic power goes back drastically, quadratically actually. And this also entails a performance hit, so you get slower silicon, but this you can recover by actually going to parallel execution. Now, to do this parallel execution, what you need is very small cores with, if you will, naked level 1 interfaces for the memory exposed. So we can actually cluster a lot of these small cores at the very tightly coupled level and group them into larger compute clusters. There's also other angles like managing leakage and PVT variability, which we won't go into. And to do this, we actually need a very strong ISA, and we need full access to the features of a processor core, because we really want to tune the pipeline of the processor, and we want to play with every detail. So RISC-V is a very good starting point, because we can take that and create a new open microarchitecture around that, which is our RISC core, which we will talk about some more. So basically, as I said, going beyond the 32-bit precision or 64-bit precision standard, machine learning offers, as we heard, a lot of flexibility in bit precision, and you can go to much smaller arithmetic widths very easily. So a kind of natural extension is to go to two-way and four-way SIMD vectorization, which gives you an automatic 2x or 4x efficiency and memory capacity speed up or bump if you don't need the precision. And so RISC-V is an awesome ISA to start to do that, because it has been designed for extensibility by construction. So what we did is we took the RISC-V baseline spec, the RV32 IMC, and this was our V1 implementation. Then we went ahead and added V2, which contained hardware loops, post-modify load stores, so you can do your pointer bumping, multiply, accumulate, etc. And then went ahead to version 3 in another iteration to add these SIMD operations, dot product shuffling, and some fixed point for embedded machine learning applications. This actually pushes the core up in size, so it actually goes from 25 kilogate equivalents to 40 kilogate equivalents, so that's a 1.6x increase. Now the question is it actually worth it? And so if we look at a very small example, this is a very simple pointwise addition on a vector. If you do this in plain RISC-V, you end up with roughly 11 cycles in the machine being consumed to produce one output element of the vector. Now, if we add our post loads and store increment operations, this goes back to down to 8 cycles per operation, because we can get away with the pointer fiddling. If you use hardware loops, we can actually also do away with all the bookkeeping for the loop indices, which makes it go down to 5 cycles per output. And then if you add packed SIMD on top, because say you don't need the full 32-bit precision, but only 8 bits, this actually increases because you get the free 4x speed up also from SIMD. So this goes to 1.25 cycles per output produced. So actually, this is a 10x speed up on a 2D convolution, which is fairly common in ML, as you're aware, I'm sure. So this is definitely worth it. Now, actually going beyond that, if we start from the one core example and we add our extensions, we get a 2x speed up. But then we also need to recover performance, which we lose due to going near threshold. And the nice thing about machine learning is that this has very close to ideal speed up, so we can recover a lot of lost performance and actually exceed the original design's performance. So this goes up to 75x of speed up if you combine all the effects on top. This has been released as the Pulp NN, which is the Pulp neural network library, which handles DNN training on Pulp cores. So actually, as you look at the evolution of the Pulp species of chips, you can actually see that as we add these extensions to the ISA, the peak efficiency of the chips goes up significantly. So from 60 gigaops per watt all the way up to 385 gigaops per watt. So in Pulp v3, this is a die shot of that chip. We actually are down to 2.6 picojoules per op, which is already very close to this goal we set at the beginning. You can actually take this much further. You can add a microcontroller class core to that, which can on demand turn on and off this cluster if you need the processing power or not. And this allows you to create a highly energy proportional computing system, which goes from 72 microwatts if you don't use the system at all the way up to 153 milliwatts if you need the full brunt of compute power, which is on that chip. There's also other angles what you can do. As we heard this morning, is specialization. If all things are being equal, is the thing that always wins. And we, of course, observe this as well. So if we have these cores with the level 1 memory interfaces exposed and attached to a tightly coupled memory, there's nothing stopping us from adding dedicated hardware accelerators to that interconnect to also leverage this gain that you get from a fixed function pipeline when operating on data in the shared memory. So a good example of this shared unit that you could build is a floating point unit, which is shared among cores, or is a streaming approach, streaming kind of a processor which operates on the memory directly. And we've actually developed a floating point unit which supports the RISC-V F&D extension. It's fully IEEE compliant, it's open source, you can find it on GitHub. It uses the separate float register file as mandated by RISC-V, but it's fully configurable. So you can go down to completely different floating point formats. So for example, the IEEE half precision format, or the B floats of the TPU, or even a custom 8-bit binary format, which coincides to be the same as Microsoft's approach there. This, of course, also opens the avenue for packed SIMD, because you're now using smaller formats. And there's other angles that we explored, like unified floating point integer register file, which in some cases can save significant performance. So if you combine all of this into a big system, so you take Pulp cluster, microcontroller core, and a hardware convolution engine as a shared accelerator, what you get is a chip which is called GAP8, which is Greenwave's Technology's commercial implementation of this Pulp system. And what this gives you is a significant edge over existing microcontroller-style processors, which you can use for your deep learning applications. And by using this fixed function pipeline, gives you a lot of additional energy efficiency gains on top. And a PhD student in our group has actually taken this GAP8 processor and has mounted it on a nano drone, which is a very small UAV, where this chip now runs the DroneNet neural network. And in doing so, this drone is actually capable of doing fully autonomous flight and obstacle avoidance without any human operator, all computation running entirely on the drone, driven by this high energy efficiency that the Pulp processors offer. There's a YouTube link for you to visit if you want to see a video of that thing flying around the lab. So talking about the cores a bit, the RISC-V core, this is our 32-bit core. This is our main workhorse. This is what actually drives most of the Pulp chips. It's a 4-stage pipeline core, which is optimized for energy efficiency. It's around 40 kilogates, 30 logic levels. Core mark is around 3.2. And it has these various Pulp extensions that we added to the instruction set architecture. So these include like the post-increment load and stores, harder loops, ALU extensions, multiply, accumulate on various bit with SIMD instructions, which are packed, so you get 2x or 4x SIMD vectorization. And this allows you to evaluate such an expression as you see at the bottom in one cycle and operation. And these also come with the accompanying GCC extensions. Now, on top of that, we also wanted to have a smaller core for small control tasks. So what we did is we re-engineered RISC-V and redeveloped the pipeline to build zero and micro RISC-V, which are basically a 2-stage pipeline processor with a very simplified register file. And they are roughly at half or a quarter the size of RISC-V. And we use these a lot as SoC level controllers in the Pulp systems. And now as a final step, we also tapped into the world of the 64-bit cores. So in the first 4 years of the Pulp project, we used only 32-bit cores. And my boss, Lucas, said once famously that we will never, ever build a 64-bit core. And that was motivated by the fact that most IoT applications work well with 32 bits, and the typical 64-bit core is much more than just 2x the size of a 32-bit core. So there's not much to be gained at first glance. But times change, and having a 64-bit Linux-capable core is actually interesting because it allows you to share the same address space as very big mainstream processors. We use that in several systems. There's a lot of interest from the security community to have such an open core, and there are other open research questions that we can answer with this. So enter the Ariane core, which is our latest addition to the core lineup, which is a 64-bit core. It's a 6-stage pipeline with integrated caches, hardware page table walkers, and supports the privilege spec. And we've actually taped this out in 4 different silicon chips. And actually, if you deploy this to a FPGA board, you can boot Linux on it, which is a very nice thing to have your core do. And we actually tried to go beyond that, and this is where the V extension comes in of the RISC-V ISA, where we add to Ariane the ARA coprocessor, which is basically an implementation of the Krste vectorization extension of RISC-V, which allows you to leverage a lot of additional compute power. So just the cores doesn't make a really good system where you can do research. So what we actually do is these cores, they're just a starting point. What we do is we add on top a lot of peripherals so we can talk to the outside world and move data. And we add the interconnects so we can formulate a memory hierarchy around those cores, which allows for interesting systems to be built. We add accelerators like the hardware convolution engine for fixed function pipelines, some streaming accelerators for floating point, crypto, etc. And then what we do is we combine all of these ingredients into different platforms, which I can show you now quickly. So the simplest version is a single core platform. And our first single core platform was the Pulpino, which is basically a very simple design meant for a quick release of the work we have been doing. It has separate data and instruction memories. It's not meant to be a hardware architecture, but it just makes it easy to develop in hardware. And you can plug in any of our 32-bit cores into that system. Then on top of that, we developed another single core system, which is Pulpissimo, which is basically an improved version of that. It has a unified data and instruction memory. This is thanks to it sharing a lot of the infrastructure with the cluster-based Pulp Pulp architectures, which also allows you to have hardware acceleration in that. It has an advanced DMA to move data between IOs, so you can really take full advantage of that. And we use this a lot as an SoC or kind of fabric control in larger Pulp systems. And actually, our main Pulp systems that we built, they're all cluster-based, not just single core. So the way we do this is we start with RISC-V processors. We attach them to what we call a tightly coupled data memory. It's basically an explicitly managed L1 scratchpad memory. It's attached to the cores via a combinatorial single-cycle latency network. Via the same network, you can actually go out of the cluster into what we call the SoC domain. There's usually a larger L2 memory, which is slower but holds bigger chunks of data and the program. There's a DMA to move data back and forth between them while the processors operate. The processors have a shared instruction cache attached, which fetches data from the SoC domain. You can have hardware accelerators to do fixed function work at the high energy efficiency, and we have an event unit to actually manage resources and allow for fast sleep and wake up. Then on top of that, you can actually take this SoC domain and you can add a full microcontroller system there, Pulpissimo, for example, which can actually turn off the cluster and run very simple tasks at the same time. And now finally, what you can do if you want to go beyond a single cluster, because the things in a cluster only scale to a certain degree. So to go beyond that limit, you have to basically go multi-cluster. One example of that is Hero, for example. This is our heterogeneous research platform. And it's based on an ARM-based host processor. This can be an ARM Juno SoC board with an FPGA attached, or it can be any of the sync devices that you can buy from Xilinx. And the idea is that in the FPGA fabric, you have a multi-cluster Pulp accelerator attached, which shares memory space with the host and allows for very tightly coupled and efficient offloading of data. We also had a recent collaboration with Princeton University where we started to work with them on their Open Python system, which is basically a scalable network on chip with a coherent last level cache. This allows you to assemble a large grid of tiles which contain a processor core each. Their original design used the OpenSpark T1, and they could assemble these big multi-core systems based on that. And we actually managed to replace this OpenSpark T1 with an Ariane core. And this you can now assemble into these large systems using OpenPython. This has been released in a bare metal version and is now being worked on. And depending on what kind of FPGA you have, you can actually deploy the system there with various configurations. So if you have a smaller board, you can go for 2 cores, or if you have a bigger board, you can go up to 4 or 16 Ariane cores working with each other. And you can boot Linux on that. It works well. You can see every Ariane core as a separate processor there, and you can even play Tetris on that over the network. So it's actually pretty neat setup. So we talked a lot about the platform and the chips that make those platforms, but let me also show you a bit what we actually do, the chips we do. And I can tell you, we do love to tape out silicon and actually build chips and measure how good they are after manufacturing. So we have designed roughly 25 ASICs, actually more than that, which are based on this Pulp architectural template. And a lot of those ASICs are meant to go on the IC tester. They're only there for characterization mainly. We evaluate various efficiency numbers there. They don't have many peripherals, and they're not meant to be deployed in bigger systems. We also have other ASICs which are meant to go more into the application domain, where there are more peripherals. You have an SPI interface or a camera interface to talk to the outside world, or you have more on-chip memory to actually hold more data and do more significant processing. This is what goes onto this nano drone, for example. So you can actually go out and buy a commercial development board with Pulp technology. For example, there's the Vega board from openisa.org, which is a microcontroller board which is based on RISC-V and zero RISC-V. Or you can buy the Gapwino board from Greenwaves, which contains versions of the Gap processor, which is a Pulp cluster system with 8 processors in the cluster and RISC-V core attached. So let me give you a very quick illustrated tour of the history of ASICs that we've developed. So kind of the seminal cores, the Pulp, original Pulp 1, 2, and V3 cores, they were all developed in 28 nanometer FTSI technology. They had open RISC cores in them back in the day, and we explored various architectural things and technological things with them. Then we moved forward towards more system chips, which were meant for actual applications and to be put on application boards. These contained more peripherals, such as SPI, I2C, GPIOs, etc. So Mia Wallace and Fulmin that you see there, they still used open RISC cores. They were taped out in UMC's 65 nanometer technology. And then with Honey Bunny, we moved more towards the smaller technology sizes. So this was done in GlobalFoundries 28 nanometer. And this was the one that used the first RISC-V core. And all of those chips have our own custom FLLs in there, so we can actually run them at speed. We also combined Pulp with analog front ends for biomedical applications. These were designed in collaboration with Professor Huang's analog group at ETH Zurich. These chips were taped out in SMIC's 130 nanometer technology because we had these analog IPs that we needed to fit there. And there, as you can see, the first few were also open RISC based, and now we've moved to RISC-V after the cores have matured and these systems have grown up. Now, back in 2018, we then started to push for a new generation of chips where we actually not only had these big cluster systems, but we also added these microcontroller style system on chip parts to that. This is, for example, the Mr. Wolf chip that we did, which contains 9 RISC-V cores. So there's 8 RISC-V cores, which actually do the number crunching. There's a 0 RISC-V, which does a lot of the controller management. We have a multi-cluster Pulp implementation, and we have an Ariane-based microcontroller, which were also taped out in various technologies. Then we tried to push for even larger system chips. This is still back in 2018. We had 3 runs done in GlobalFoundries 22 FTX. They're around 10 square millimeters. There's a combination of RISC-V cores and Ariane cores that we tried in various configurations. There's an implementation of a floating point streaming accelerator, which allows you to do highly efficient training of machine learning models on these small devices. And we even had an embedded FPGA in a collaboration with QuickLogic implemented on such a device. And now the next frontier, basically in 2019, are these 3 chips, which are currently in the process of being manufactured, which take this even further. They contain for example, various combinations of RV32 cores extended with streaming enhanced ISA to go for maximum floating point throughput. And we have a heterogeneous SoC, which combines the Ariane 64-bit processor with the Pulp cluster 32-bit to form this heterogeneous system with a custom DRAM controller. So we basically firmly believe in the open source movement. So the whole Pulp platform was first launched in February 2016 on GitHub. All our development on the cores is done openly on those repositories. It's mostly done in System Verilog directly. And we get many contributions from many different groups back via this platform. And we firmly believe that open hardware is actually a necessity. It's not just an ideological crusade that you can go out to. So the way we design ICs has changed significantly. A lot of the big chunks that you need to do is now infrastructure. You need to get processors, peripherals, memory systems. Everything is considered an infrastructure, and you have very few groups on the planet who can actually fully build a complete IC from scratch. And what you need is high-quality IP blocks to do that. And to do that, we need an easy and fast way to collaborate with other people. And this is currently quite annoying because you need complicated agreements among the parties in very convoluted constellations usually. And in many cases, this is too difficult for academia or even small enterprises to try out. And of course, hardware is critical for security, also in the light of the recent developments, and we need to make sure that it is secure. And one way to do this is being able to see inside the hardware. So you can actually audit your chips yourself because they are open. And you can draw your own conclusion if what you get is actually what you wanted or what the manufacturer intended. Also, this tendency of us to try to manufacture these chips and go to silicon, and the openness of the hardware is a big part of what fuels Pulp's success. And we have many companies, which we are aware of, that actively do use Pulp. And when we talk to them, they always tell us that they value that it is silicon-proven, so they can start from the design and have some reassurance that this has actually already been working on actual silicon. And they like that it is permissively open source licensed, so they can also use it for commercial projects on their own. Now, the cores grow up, they are research projects. There are babies, we nurture them and we develop them and we try to extend them, but at some point they kind of outgrow us. And this is why we've teamed up with a few other players. For example, Low Risk has agreed to maintain the micro and zero risky cores as a new core, which is called IBEX, which unifies these two configurations, but you can still pick from the two. They have their own vested interest in using the core in their projects. They have a team that can provide support. And we, as University of Zurich and the ETH of Zurich and the University of Bologna, we will still contribute to this core. But the main maintenance and support will move to Low Risk. And of course, we need a small mascot for that, but our cores grow, and at some point they have to leave the house. And furthermore, quite a few players from academia and from industry have teamed up to create the nonprofit Open Hardware Group, which is basically a consortium which aims to provide a family of cores, which is called Core V, which are open source. They contain related IPs and tools to actually design open source systems here around the RISC-V setup. And the Open Hardware Group will actually take over the RISC-V core. They will try to move this into what they call Core V, which is this family of cores that they develop, and they will maintain that. And with this, I'm at the end of my talk. This was a very quick and deep dive into our research projects, our tape-out projects, and what RISC-V enables us to do and what we can give back to the community. It's a different approach than Rocket and Boom. But this has been everything I have to tell you. So I would suggest, I have only a minute left, so I would suggest that if you have any questions, it's probably best if you talk to me afterwards during the reception. Is that okay? Okay, so thank you very much. Have a very good evening. Enjoy your reception, and see you later.